Hello there, and welcome to Midnight Science. I'm so glad you found your way here, because tonight we're going to explore the most extraordinary moment in history. The moment before there were any moments at all. Before stars, before darkness, before space itself. We're drifting back to the Big Bang, to that first flash of creation when everything, everywhere, all at once, began its journey into existence. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the universe's birth. Not just one galaxy or star, but the explosive beginning of all reality. We'll move gently from fact to fact, learning about quantum beginnings, cosmic inflation, the first light, and the ancient echoes that still fill the sky. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Also, I'd love to know where you're tuning in from and what time it is there. It's fascinating to see how these videos connect people from around the world. Now, if you're ready, let's begin our journey back to the moment when time itself was born. The universe began from something smaller than an atom. It's hard to imagine, but everything we see, every star, every galaxy, every particle of light, once occupied a space smaller than the tiniest thing you can picture, smaller than a grain of sand, smaller than a single atom, smaller even than the nucleus at the heart of that atom. This unimaginably dense point contained all the energy and all the potential that would become our universe, not sitting in space because space didn't exist yet, not waiting in time because time hadn't started. It simply was. And then, in an instant that defies every rule of our everyday experience, it began to expand, not into something, but creating space itself as it went. The Big Bang wasn't an explosion in space. It was the explosion of space. A flowering of reality from a seed too small to see, too strange to fully understand, and yet, somehow, it happened. And here we are, 13.8 billion years later, still feeling its echo. Time itself began with the Big Bang. When we ask what came before the Big Bang, we're asking a question that might not have an answer, not because we don't know enough, but because before might not mean anything in this context. Time, as we understand it, began with the Big Bang. It emerged alongside space, matter, and energy, all woven together in a single cosmic birth. Before that moment, there was no clock ticking, no sequence of events, no earlier or later. Some theories suggest a different kind of reality existed, a quantum realm where time behaves differently or doesn't exist at all. Others imagine previous universes or cycles of creation. But in most models, the Big Bang marks the start of time's arrow, the moment when past, present, and future became meaningful concepts. It's a strange thought, not just that the universe had a beginning, but that beginning itself had a beginning. And before time, there was only, well, nothing. Or perhaps something we don't yet have words for. The universe was once unimaginably hot. In the first fraction of a second after the Big Bang, the universe wasn't just hot, it was incomprehensibly hot. Temperatures reached trillions upon trillions of degrees, far hotter than the core of any star that would ever exist. At these extreme temperatures, matter as we know it couldn't form. There were no atoms, no molecules, not even stable particles. just pure energy seething and roiling in an impossibly dense state. This primordial heat came from the Big Bang itself, from the violent release of energy as space began expanding. As the universe grew, it cooled, but in those earliest moments, it was a blazing furnace of creation. Nothing could survive such heat today, but back then, it wasn't destructive. It was creative. From that cosmic fire, everything would eventually emerge. The forces that govern reality, the particles that build atoms, and eventually, after billions of years of cooling and settling, the gentle warmth of a star like our sun. All of it traces back to that first searing moment when the universe burned brighter than anything that would ever burn again. The first particles appeared in less than a second. As the universe expanded and cooled from its initial inferno, something remarkable happened. Within the first second, possibly within the first trillionth of a second, the first fundamental particles began to appear. Quarks and gluons, the building blocks of matter, emerged from the cooling energy soup. These weren't atoms yet, not even close. They were simpler, more fundamental, the raw ingredients from which everything else would be built. As temperatures dropped further, quarks combined in groups of 3 to form protons and neutrons. Electrons appeared. Photons, particles of light, flooded the universe. All of this happened in less time than it takes to blink. The universe at 1 second old was unrecognizable compared to today, but it already contained the seeds of stars, planets, and life. These first particles, forged in the heat of creation, are still with us. The protons in your body, the electrons flowing through your nerves, they're the same fundamental particles that appeared in the universe's first moment. You are made quite literally from the opening chapter of cosmic history. Cosmic inflation explains why the universe looks smooth. One of the deepest mysteries about the Big Bang is why the universe looks so uniform. When we observe the cosmic microwave background, the afterglow of the Big Bang, we see that it's remarkably smooth. Temperature variations are tiny, just fractions of a degree across vast distances. But if the universe simply expanded at a steady rate, different regions would never have had time to interact and even out. They'd be wildly different from each other. So how did the universe become so smooth? The answer, according to most cosmologists, is cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This sudden stretching smoothed out any irregularities, like pulling a wrinkled sheet until it's flat. When inflation ended, the universe continued expanding, but at a slower rate. This brief but dramatic episode explains not only the universe's smoothness, but also its large-scale structure. And it did all of this in less than a trillionth of a second. A cosmic ironing that set the stage for everything that followed. Quantum fluctuations became the seeds of galaxies. During inflation, when the universe was expanding exponentially, something subtle but profound was happening. At the quantum level, reality is never perfectly smooth. Tiny random fluctuations appear and disappear constantly. Bubbles of uncertainty built into the fabric of existence. During inflation, these quantum jitters were stretched to cosmic proportions. What began as microscopic variations became vast differences in density across the early universe. These density fluctuations, though tiny, were enough. In regions where matter was slightly denser, gravity pulled in more material. Over millions and billions of years, these slight overdensities grew into the structures we see today. Galaxies, clusters, and the vast cosmic web all trace back to quantum fluctuations, random events smaller than an atom, magnified by inflation into the architecture of the cosmos. It's a humbling thought. The grand structure of the universe, all the galaxies and stars and worlds, began as quantum noise, randomness stretched into pattern, chaos giving birth to order. And from those tiny trembling seeds, the universe grew into the vast, intricate tapestry we observe today. The universe doubled in size. Many times in its first second, when we say the universe expanded after the Big Bang, we're not talking about a slow, gentle growth. In the first second, particularly during the inflationary period, the universe doubled in size over and over again in rapid succession. It didn't just grow, it exploded outward, each doubling happening in a time span too short to comprehend. Some models suggest the universe doubled in size at least 60 times during inflation, possibly more. Each doubling meant the universe became twice as large in every direction. After 60 doublings, a region the size of a subatomic particle would be stretched larger than the observable universe today, all in a fraction of a second. This exponential growth is hard to visualize, but it's the key to understanding how the universe went from incomprehensibly small to incomprehensibly vast, not gradually, but in a sudden, violent burst of expansion. A cosmic explosion not of matter, but of space itself. And when it was over, the universe was already enormous, cooling, and ready for the next chapter. Protons and neutrons formed in the first microsecond. As the universe continued to cool, quarks, which had been moving freely in the hot plasma, began to stick together. This happened around 1 microsecond after the Big Bang. Quarks combined in groups of 3 to form protons and neutrons, the particles that would eventually make up the nuclei of atoms. It was a critical transition. Before this moment, the universe was too hot for these composite particles to hold together. After this moment, the building blocks of atomic matter were in place. Protons are positively charged. Neutrons have no charge. Together, they would later combine to form the nuclei of hydrogen, helium, and other light elements. But for now, they simply existed, drifting in a sea of electrons, photons, and neutrinos. The universe was still far too hot for atoms to form. That would take hundreds of thousands of years. But the first step had been taken. The first stable structures had appeared. And from this moment forward, the universe would gradually cool and settle, allowing more complex structures to emerge, layer by layer, like a sculpture slowly revealing itself. The universe was once a glowing plasma. For the first few 100,000 years after the Big Bang, the universe was opaque, not dark, but glowing. It was filled with a hot, dense plasma of protons, electrons, and photons all mixed together. Light couldn't travel far in this state. Every photon that tried to move forward would immediately collide with an electron and scatter in a new direction. It was like trying to see through fog, except the fog was everywhere, filling all of space. This glowing plasma was the universe's infancy. No stars yet, no galaxies, no structure. Just a thick, glowing soup of particles slowly cooling as space expanded. The temperature was still thousands of degrees, too hot for atoms to form. But as time passed, the the universe continued to expand and cool. Eventually, it would reach a turning point, a moment when the plasma cleared and light could finally travel freely. That moment, known as recombination, would mark the end of the universe's opaque phase and the beginning of transparency. And the light released at that moment is still traveling today, stretched and cooled, carrying the story of the universe's earliest visible moment. The first atoms formed 380,000 years after the Big Bang. For hundreds of millennia, the universe was too hot for atoms to exist. Electrons couldn't stay bound to nuclei because the ambient energy kept knocking them loose. But around 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin, cool enough for a change. Electrons began to settle into stable orbits around protons and atomic nuclei. The first atoms formed mostly hydrogen, with some helium and trace amounts of lithium. This event is called recombination, though it's a bit of a misnomer since the electrons and nuclei were combining for the first time, not recombining. With atoms now stable, something remarkable happened. The universe became transparent. Photons, which had been constantly scattering off free electrons, were suddenly free to travel without obstruction. Light could finally move through space unhindered. The universe, which had been glowing and opaque, cleared like a fog lifting, and the light released at that moment, the first light to travel freely, is what we detect today as the cosmic microwave background, a faint, cool glow from the moment the universe opened its eyes. The cosmic microwave background is the oldest light we can see. Turn on a radio between stations and you'll hear static. A tiny fraction of that static, less than 1%, is actually noise from the Big Bang. It's the cosmic microwave background, or CMB, the faint afterglow of the universe's birth. This light was released 380,000 years after the Big Bang, when atoms first formed and the universe became transparent. Back then, it was a bright glowing light, but as the universe expanded, that light was stretched, its wavelength growing longer and longer until it became microwaves. Today, the CMB fills the entire sky. It's everywhere, a faint whisper of radiation at just a few degrees above absolute zero. We can't see it with our eyes, but sensitive instruments can detect it. And when we do, we're looking at the oldest light in the universe, a snapshot of the cosmos when it was just a baby. The CMB is one of the strongest pieces of evidence for the Big Bang. It matches the predictions perfectly. Its temperature, its smoothness, its tiny fluctuations, all of it tells a consistent story. The universe began hot and dense, then expanded and cooled. And the light from that moment is still here, still glowing, still carrying the memory of creation. The universe had no stars for hundreds of millions of years. After recombination, when the first atoms formed and the universe became transparent, you might expect stars to appear quickly, but they didn't. For hundreds of millions of years, the universe was dark. It was filled with hydrogen and helium gas, slowly drifting through space. But no stars had ignited yet. This period is sometimes called the Cosmic Dark Ages. Not because the universe was completely lightless, the CMB still glowed faintly, but because there were no stars or galaxies. Just vast clouds of gas filling the expanding void. Gravity was at work though. Slowly, over time, these gas clouds began to clump together. Denser regions pulled in more material. Eventually, these clumps became dense enough and hot enough for nuclear fusion to begin. And when that happened, the first stars ignited. These early stars, known as population III stars, were massive, hot, and short-lived. They lit up the universe for the first time since recombination, ending the Dark Ages and beginning a new era, the era of starlight. But until that moment, the universe was a quiet, dark expanse, waiting for the first spark to ignite. Hydrogen and helium were the first elements in the first few minutes after the Big Bang. The universe was still incredibly hot, but cool enough for something important to happen. Protons and neutrons, which had formed earlier, began to stick together to form the nuclei of light elements. This process, called Big Bang nucleosynthesis, created hydrogen, helium, and tiny amounts of lithium. Most of the universe remained hydrogen, the simplest element, just a single proton. But about 25% became helium, 2 protons and 2 neutrons bound together. Trace amounts of deuterium, a heavy form of hydrogen, and lithium also formed. These were the only elements made in the Big Bang. Everything else, carbon, oxygen, iron, gold, all the heavier elements would have to wait. They'd be forged later, inside stars, through nuclear fusion and supernova explosions. But hydrogen and helium were the original ingredients, the raw materials of the early universe. And even today, they remain the most abundant elements in the cosmos. The stars you see burning in the night sky are still mostly hydrogen and helium, the same elements born in the first few minutes of time. Ancient chemistry, still present, still glowing. The universe is still expanding today. The Big Bang wasn't just a one-time event. It's still happening in a sense. The universe is still expanding, and it's been doing so for 13.8 billion years. Galaxies aren't just sitting in space. They're moving away from each other as space itself stretches. This expansion was first discovered by Edwin Hubble in the 1920s. He observed that distant galaxies were redshifted, meaning their light was stretched to longer, redder wavelengths. The farther away a galaxy was, the faster it seemed to be moving away. This wasn't because the galaxies were flying through space. It was because space itself was expanding, carrying the galaxies along with it. Since then, we've learned that the expansion is accelerating. Driven by something called dark energy, the universe is growing faster and faster. Eventually, distant galaxies will be moving away from us faster than light, and we'll lose sight of them forever. But for now, the expansion continues. A slow, steady stretching that began at the Big Bang and hasn't stopped. The universe, it seems, is still in the process of becoming, still unfolding, still growing. A work in progress, 13.8 billion years old and counting. We can't see the moment of the Big Bang itself. As far back as we can observe directly, we hit a wall. Not a physical wall, but an observational one. The cosmic microwave background, released 380,000 years after the Big Bang, is the oldest light we can detect. Before that, the universe was opaque, filled with hot plasma that scattered light. We can't see through that fog. So the Big Bang itself, the very first moments, remain hidden from direct view. We can't take a picture of it. We can't capture its light. Everything we know about the Big Bang comes from indirect evidence. The CMB, the expansion of the universe, the abundance of hydrogen and helium, the large-scale structure of galaxies. All of these pieces fit together into a consistent picture. But the moment itself, that first instant when everything began, is beyond our current reach. Some scientists hope that future detectors might pick up primordial gravitational waves, ripples in space-time from the first moments of inflation. If we could detect those, we'd be sensing the universe at an even earlier stage, closer to the Big Bang itself. But for now, the very beginning remains a mystery, tantalizingly close, but just out of sight. A story we can infer, but not yet fully witness. The Big Bang happened everywhere at once. One of the most common misconceptions about the Big Bang is that it happened at a specific location, that there's some spot in space where it all began. But that's not quite right. The Big Bang didn't happen at a point in space. It happened everywhere, all at once. Space itself was born in the Big Bang, and it began expanding from every point simultaneously. There's no center to the expansion. If you could rewind the universe, every location would converge back to the same initial state. Everywhere was once the same place. When we say the universe is expanding, we don't mean it's growing outward from a center like a balloon inflating from a single spot. It's more like the surface of a balloon being inflated, where every point on the surface moves away from every other point, but there's no center on the surface itself. This means the Big Bang happened here, and it happened where the most distant galaxies are now, and everywhere in between. You're standing or lying at the site of the Big Bang. So is everyone else. So is everything. It's not out there somewhere. It's here. It's everywhere, and always has been. The Big Bang wasn't an explosion in space. Despite the name, the Big Bang wasn't really a bang. It wasn't an explosion that threw matter outward into empty space. Space itself emerged from the Big Bang, expanding and carrying matter and energy along with it. There was no surrounding void into which the universe exploded. No stage on which the drama unfolded. The universe created the stage as it went. Think of it less like a bomb going off and more like a photograph being developed, slowly revealing detail layer by layer as it grows. Or imagine the universe as a loaf of raisin bread baking in an oven. As the bread rises, the raisins, representing galaxies, move apart from each other, not because they're flying through the dough, but because the dough itself is expanding. That's closer to what the Big Bang is like, a gentle, continuous expansion, not a violent scattering. The term Big Bang was actually coined by astronomer Fred Hoyle in 1949, somewhat mockingly. He didn't believe in the theory and used the name to make it sound absurd, but the name stuck. And now we're left with a term that doesn't quite capture what really happened. Not a bang, but a blossoming. A slow, vast unfurling of space, time, and everything within it. The universe was once smaller than a grain of sand. It's almost impossible to wrap your mind around, but the entire observable universe, everything we can see in any direction, was once compressed into a region smaller than a single grain of sand. Not just the matter, but the space itself. All the stars, galaxies, planets, black holes, and the space between them squeezed into something unimaginably tiny. This wasn't just dense, it was beyond dense. The laws of physics as we know them break down under such conditions. Gravity, quantum mechanics, space-time itself all behave in ways we don't fully understand. That's why scientists can't yet describe the very first instant of the Big Bang. We need a theory of quantum gravity, something that unites general relativity with quantum mechanics to truly grasp what happened. But we know this much. From that tiny, unimaginably compressed state, the universe expanded. And as it did, it carried with it all the potential for everything we see today. Stars, life, thought, wonder, all contained in a seed smaller than you could hold between your fingers. It's a humbling, dizzying thought, but it's where we all come from. Infinitely small, then suddenly vast. No one knows what caused the Big Bang. For all we've learned about the Big Bang, one question remains unanswered. What caused it? What set it in motion? Why did it happen at all? These are among the deepest questions in cosmology, and we simply don't have definitive answers yet. Some theories suggest the Big Bang was a quantum event, a random fluctuation in a pre-existing field. Others propose it was the result of a previous universe collapsing and rebounding. Some physicists think our universe might be one of many in a vast multiverse, each with its own Big Bang. And still others suggest that asking what came before might not make sense if time itself began with the Big Bang. The truth is, we may never know. The conditions at the very beginning are so extreme, so far beyond anything we can recreate or observe, that we're left with educated guesses and mathematical models. But that doesn't diminish the wonder. If anything, it deepens it. The universe began, and here we are asking why. The question itself is part of the story. A universe contemplating its own origins. And perhaps that's as close to an answer as we'll ever need. The universe may have no edge or boundary. If the universe is expanding, does that mean it has an edge? A place where space simply ends? Not necessarily. Current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. If the universe is infinite, it has always been infinite, even when it was compressed to a tiny point. Infinity times zero is still a kind of infinity in mathematical terms. If it's curved and closed, like the surface of a sphere, you could travel in a straight line forever and eventually return to where you started, never encountering an edge. Both possibilities are strange to think about. An infinite universe means there's no center, no boundary, just endless space in all directions. A closed universe means it's finite in size but has no edge, like walking around the Earth's surface. Either way, the universe doesn't have a border you could reach or a wall you could touch. It's seamless, continuous, and possibly without end. And somewhere in that vastness, here we are. Not at the center, because there is no center. Just one small region among countless others, all equally valid, all equally part of the whole. Antimatter was created alongside matter. In the first moments after the Big Bang, matter and antimatter were created in equal amounts. For every particle of matter, a proton or electron, there was a corresponding antiparticle, an antiproton or positron. When matter and antimatter meet, they annihilate each other in a burst of energy. So the early universe was filled with constant creation and destruction, particles appearing and vanishing in violent collisions. If matter and antimatter were truly equal, they should have completely annihilated each other, leaving behind only energy. But that didn't happen. Somehow, there was a tiny imbalance. For every billion pairs of particles and antiparticles, there was one extra matter particle. When the annihilation ended, that tiny excess remained, and that leftover matter is everything we see today. Stars, galaxies, planets, you. Why was there an asymmetry? We don't fully know. It's one of the great unsolved mysteries of cosmology. Something in the laws of physics must favor matter over antimatter, but we haven't pinpointed exactly what. What we do know is this: if the universe had been perfectly balanced, nothing would exist. No stars, no life, no observers, just empty, cooling radiation. But because of a tiny imbalance, matter survived. And here we are, the descendants of that 1 in a billion surplus, asking how we came to be. Neutrinos from the Big Bang are all around you. Right now, trillions of particles are passing through your body. You don't feel them, you don't see them, but they're there. These are neutrinos, ghostly particles that barely interact with anything. Most were created in the first second after the Big Bang, and they've been streaming through the universe ever since. Neutrinos are incredibly light and electrically neutral. They move at nearly the speed of light and pass through matter as if it isn't there. A neutrino could travel through a light year of solid lead without hitting anything. The Big Bang produced an enormous number of them, and they're now part of the cosmic neutrino background, a faint sea of particles filling all of space. These relic neutrinos have cooled to almost absolute zero, making them nearly impossible to detect. But they're still here, a quiet remnant of the universe's fiery birth. Every second, billions pass through your body without leaving a trace. They carry information about the early universe, encoded in their motion and energy. If we could detect them, we'd have a new window into the Big Bang itself. But for now, they remain elusive, silent witnesses to creation, drifting unseen through the fabric of the cosmos. The universe went through a particle soup stage. In the first microsecond after the Big Bang, the universe was so hot and dense that matter didn't exist in the form we know it today. Instead, there was a seething, chaotic soup of fundamental particles. Quarks, gluons, electrons, photons, neutrinos, all bouncing, colliding, and transforming in a state called a quark-gluon plasma. In this plasma, quarks couldn't bind together to form protons or neutrons. The energy was too high, the collisions too violent. Everything was in constant flux, a roiling sea of particles with no stable structures. As the universe expanded and cooled, this plasma underwent a phase transition. Quarks began to stick together, forming protons and neutrons. The soup thickened, so to speak, and the first stable particles emerged. This transition happened quickly, in a fraction of a second, but it was a critical moment in cosmic history. Before it, the universe was a chaotic blend of fundamental forces and particles. After it, the building blocks of atoms were in place. The universe had taken its first step towards structure, order, and eventually, the complex matter that would fill galaxies, planets, and living cells. From chaos came form. From soup came substance. Dark matter was present from the beginning. As the early universe cooled and matter began to clump together, something invisible was also at work. Dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, was there from the very beginning. We don't know what dark matter is made of, but we know it exists because of its gravitational effects. It helped shape the early universe, pulling gas into dense regions where the first stars and galaxies would form. Without dark matter, the universe would look very different. Galaxies wouldn't hold together. The cosmic web of filaments and voids wouldn't have formed. Even the CMB, the afterglow of the Big Bang, shows subtle imprints of dark matter's influence. Dark matter doesn't interact with light, so it remained invisible throughout the universe's history. But its gravity shaped everything visible. It's the scaffolding on which the cosmos was built. And yet, we still don't know what it is. Particles we haven't discovered yet. A new kind of field. Something even stranger. The mystery remains. But one thing is clear. Dark matter was there at the start, and it's still here now, quietly holding the universe together. An invisible presence that shaped the story of creation from the very first page. The first 3 minutes determined most of the universe's composition. In the first 3 minutes after the Big Bang, something remarkable was decided: the balance of elements in the universe. During this brief window, temperatures were just right for nuclear fusion to occur. Protons and neutrons collided and stuck together, forming the nuclei of light elements, mostly hydrogen, about 3/4 of the total, about 1/4 helium, and tiny traces of deuterium, helium-3, and lithium. After 3 minutes, the universe cooled too much for fusion to continue. The window closed, and the ratio of elements was locked in. This prediction, made by physicists George Gamow, Ralph Alpher, and Robert Herman in the 1940s, was later confirmed by observations. When we measure the abundance of hydrogen and helium in the universe, it matches the Big Bang theory almost perfectly. It's one of the strongest pieces of evidence we have. Everything heavier than lithium, carbon, oxygen, iron, gold was made later in stars. But the bulk composition of the universe, the hydrogen and helium that fill galaxies and fuel stars, was determined in those first 3 minutes, a brief moment of chemistry that set the stage for billions of years of cosmic evolution, and all of it forged in the heat of the early universe, before the first star ever ignited. The Planck epoch is the earliest time we can describe. Scientists have traced the history of the universe back incredibly far. But there's a limit, a point before which our physics breaks down. This earliest moment is called the Planck epoch, lasting from time 0 to about 10 to the minus 43 seconds after the Big Bang. That's 0 seconds, an unimaginably brief instant. During the Planck epoch, the universe was so hot, so dense, and so small that quantum effects of gravity would have been significant. But we don't have a theory of quantum gravity yet. General relativity and quantum mechanics, our two most successful theories, don't play well together at these scales. So we can't describe what happened. We don't know what the universe was like. We don't even know if time and space existed in a recognizable form. This is the edge of our knowledge, the boundary beyond which we can't yet go. Some physicists are working on theories, string theory, loop quantum gravity, that might one day let us peer into the Planck epoch. But for now, it remains a mystery, the universe's earliest moment, hidden behind a veil of mathematical uncertainty, a beginning we can point to but not yet fully see. The four fundamental forces were once unified. Today, the universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But in the earliest moments after the Big Bang, these forces weren't separate. They were unified into a single force. As the universe expanded and cooled, this unified force began to split. First, gravity separated, then the strong nuclear force, then the electromagnetic and weak forces divided. Each separation, called a symmetry breaking, changed the rules of physics, creating the distinct forces we observe today. This idea that all forces were once one is central to many modern physics theories. Scientists call it a grand unified theory, or GUT. Some even dream of a theory of everything that would include gravity as well. We haven't achieved this yet, but we've come close. The electromagnetic and weak forces have been unified in theory and experiment, a breakthrough that earned multiple Nobel Prizes. And physicists believe the strong force joins them at even higher energies. If we could recreate the conditions of the very early universe, we might see the forces merge again. But those conditions are far beyond what our particle accelerators can reach. So for now, we study the aftermath, a fractured unity, four forces where once there was one. And in that fracturing, the complexity and richness of the universe emerged. The universe's first light was released all at once. For hundreds of thousands of years, the universe was filled with light, but that light couldn't travel freely. It was trapped, scattered endlessly by free electrons in the hot plasma. But when atoms formed, 380,000 years after the Big Bang, everything changed. The electrons settled into orbit around nuclei. The plasma cleared, and suddenly light could move. All across the universe, at roughly the same time, photons were released. They streamed outward in every direction, carrying the image of the universe at that moment, hot, smooth, and glowing. This event is called the surface of last scattering. It's the moment the universe became transparent. And the light from that moment is the cosmic microwave background we detect today. In a sense, the CMB is a photograph, a snapshot of the universe at 380,000 years old. Everywhere we look in the sky, we see this ancient light, stretched and cooled by billions of years of expansion. It's the oldest image in existence, not of a single object, but of the entire cosmos. A moment frozen in time, still glowing faintly, waiting to be observed. And every time we study it, we're looking back to a time before stars, before galaxies. A time when the universe was young, simple, and just beginning to open its eyes. The CMB has tiny temperature variations. When scientists first mapped the cosmic microwave background, they found it was remarkably uniform, almost the same temperature in every direction. But not quite. There are tiny variations, fluctuations of just a few millionths of a degree. These variations are incredibly important. They represent the seeds of all cosmic structure. Regions that were slightly denser and hotter than average. Over time, gravity amplified these differences. Denser regions pulled in more matter, growing into the galaxies and clusters we see today. Less dense regions became the voids between them. Without these fluctuations, the universe would be perfectly smooth. No galaxies, no stars, no planets. Just a thin, uniform spread of gas slowly cooling in the dark. But because of those tiny temperature differences, structure formed. The fluctuations in the CMB are a map of the early universe's potential, a preview of what was to come. And when we study them in detail, we can learn about the universe's composition, age, and geometry. These minuscule variations, invisible to the naked eye, hold the story of how the universe grew from smooth simplicity to rich complexity. They're whispers from the past, patterns written in ancient light. Space can expand faster than light. One of the strangest facts about the Big Bang is this: space itself can expand faster than the speed of light. This doesn't violate Einstein's theory of relativity, which says nothing can move through space faster than light, but space itself isn't bound by that rule. During cosmic inflation, the universe expanded exponentially. Regions of space were pushed apart faster than light could travel between them. Even today, distant galaxies are receding from us faster than the speed of light, because the space between us is stretching. We'll never see these galaxies again. Their light can't reach us anymore. Not because they're moving too fast through space, but because space itself is growing too quickly. It's a subtle but profound distinction. Motion through space versus the expansion of space. And it explains why the observable universe has a boundary, not a physical edge, but a horizon beyond which we simply can't see. Light from beyond that horizon will never reach us, no matter how long we wait. The universe continues, vast and expanding, but parts of it are forever beyond our view. The Big Bang created space, not just matter. When people imagine the Big Bang, they often picture matter exploding outward into empty space. But that's not quite right. The Big Bang created space itself. Before the Big Bang, there was no where for things to exist. Space and time emerged together, woven into a single fabric called space-time. As the universe expanded, it wasn't filling a pre-existing void. It was creating the void as it went. This is why the question what's outside the universe doesn't quite make sense. There is no outside. Space is what the universe is made of, and all of space is inside the universe. Think of it like the surface of a balloon being inflated. As the balloon grows, the surface expands. But there's no edge to the surface, no boundary where it stops. Every point on the surface is equivalent. That's similar to how space works in our universe. The Big Bang didn't happen at a location in space. It happened to space. And as space expanded, it carried matter and energy along with it, stretching and cooling, creating the vast cosmos we inhabit today. The universe's temperature has been dropping for billions of years. The universe was born hot and has been cooling ever since. In the first moments, temperatures were incomprehensibly high. As space expanded, that heat spread out over a larger volume, and the temperature dropped. By the time atoms formed, 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, still hot enough to glow orange-red. Today, billions of years later, the average temperature of the universe is just 2.7 Kelvin, barely above absolute zero. That's the temperature of the cosmic microwave background, the cooled remnant of the Big Bang's heat. That cooling isn't over. As the universe continues to expand, it will keep cooling. In trillions of years, it may approach absolute zero. Stars will burn out, galaxies will fade, and the universe will grow cold and dark. But for now, we live in a relatively warm era. Stars still burn, planets still orbit, and deep in space the faint glow of the Big Bang still lingers, a reminder of the heat from which everything began. The Big Bang theory was once controversial today. The Big Bang is the accepted model of cosmic origins, but it wasn't always. When the idea was first proposed in the 1920s and 1930s, many scientists were skeptical. Some thought the universe had always existed, eternal and unchanging. Others found the idea of a cosmic beginning too close to religious creation stories and worried it wasn't scientific. The alternative was called the steady state theory, which suggested the universe had no beginning or end. As it expanded, new matter was continuously created to fill the gaps, keeping the universe's density constant. For decades, the two ideas competed, but as evidence accumulated, the Big Bang pulled ahead. The discovery of the cosmic microwave background in 1964 was the turning point. Its existence had been predicted by Big Bang theory, and its detection was powerful confirmation. Other evidence followed. The abundance of light elements, the large-scale structure of galaxies, the age of the oldest stars. Everything fit. By the 1990s, the Big Bang had become the standard model. Today, it's supported by an overwhelming body of evidence. But science remains open. If new observations contradict the theory, it will be revised or replaced. For now, though, the Big Bang stands as our best explanation for how the universe began. We are made of star stuff, which was made in the Big Bang. Carl Sagan famously said, "We are made of star stuff." And he was right. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were forged in stars. But the story goes back further. Those stars were made of hydrogen and helium, elements created in the Big Bang. So in a way, you are made of Big Bang stuff, transformed by stars. The hydrogen that became the sun, the hydrogen in water, the hydrogen in your body. Much of it has been around since the first few minutes after the Big Bang. Its primordial material, recycled through generations of stars, mixed with heavier elements, and eventually gathered into planets and life. Every atom in your body has a history. Some are billions of years old. Others were created recently in dying stars, but all of them trace back to the same origin point, the Big Bang. You are not separate from the cosmos. You are a part of it, a temporary arrangement of ancient particles shaped by gravity, chemistry, and time into something that can think, feel, and wonder. In this sense, the universe is not just something you observe, it's something you are, a living, breathing piece of the whole. The Big Bang produced equal amounts of positive and negative charge. In the early universe, when particles were forming, nature maintained a perfect balance. For every positively charged proton, there was a negatively charged electron. For every particle with charge, there was another with the opposite charge. This balance, called charge neutrality, is a fundamental feature of our universe. If there were even a tiny excess of positive or negative charge, the electromagnetic forces would be catastrophic. Matter would repel itself violently. Atoms couldn't form. Galaxies couldn't hold together. But the universe started balanced, and it remains balanced today. Every star, every planet, every living thing is electrically neutral overall. We have equal numbers of protons and electrons. This balance was built into the Big Bang itself. As particles formed, the laws of physics ensured that charge was conserved, and that conservation has held ever since. It's one of the quiet symmetries of nature. Not dramatic, not obvious, but essential. Without it, the universe would be a very different place. And we, if we existed at all, would be constantly torn apart by electromagnetic forces. The universe may have gone through multiple phase transitions. As the universe cooled after the Big Bang, it underwent several phase transitions, moments when the laws of physics changed. These transitions are similar to water freezing into ice or boiling into steam. The physical state changes, and with it, the properties of the substance. The first major transition happened when the unified force split into gravity and the other forces. Another occurred when quarks bound together to form protons and neutrons. Yet another happened when atoms formed and the universe became transparent. Each transition released energy, sometimes in dramatic bursts. Some physicists think these transitions may have created topological defects in space-time, cosmic strings, domain walls, or monopoles, exotic structures that could still exist today, though we haven't found them yet. These phase transitions shaped the universe's evolution. They determined which particles could exist, how forces behaved, and what structures could form. And they all happened in the first fraction of a second to the first few 100,000 years. After that, the universe settled into a more stable state. The dramatic changes were over, and the slower process of structure formation began. But those early transitions set the stage. They wrote the rules the universe would follow for billions of years to come. Inflation solved several cosmic puzzles at once. Before the theory of cosmic inflation was proposed, cosmologists faced several puzzles. Why is the universe so smooth? Why is it so flat geometrically? And why don't we see exotic particles like magnetic monopoles? Inflation solved all three problems at once. By proposing a brief period of exponential expansion in the first fraction of a second, inflation explained the universe's smoothness. Any irregularities were stretched out, smoothed over. It explained flatness. The universe was stretched so much that any curvature became negligible, like how a small patch of Earth's surface looks flat. And it explained the absence of monopoles. If they were created before inflation, they'd be diluted to undetectable levels by the expansion. Inflation was proposed by physicist Alan Guth in 1980 and refined by others in the years that followed. It's not proven yet. We don't have direct evidence of the inflationary period, but it fits the observations so well that it's become a central part of the Big Bang model. If we could detect primordial gravitational waves, ripples in space-time from inflation itself, that would be strong confirmation. Experiments are searching for them now, and if they're found, inflation will move from a compelling idea to an established fact. For now, it remains our best explanation for why the universe looks the way it does. The observable universe is just a tiny part of the whole. When we talk about the observable universe, we mean the region of space from which light has had time to reach us since the Big Bang. That's a sphere about 93 billion light years across, centered on Earth. But the entire universe, the whole thing, is almost certainly much larger, possibly infinite. The observable universe is just the part we can see. Beyond that boundary, the universe continues. More galaxies, more stars, more space. But their light hasn't reached us yet, and because of the universe's accelerating expansion, it never will. We're confined to observing only a small patch of reality. This means there could be entire regions of the universe, vast beyond imagination, that we'll never know anything about. Different histories, different structures, perhaps even different conditions. And if the universe is infinite, then the observable part is an infinitesimally small fraction of the whole. It's a humbling thought. Everything we can see, all the galaxies and cosmic wonders, is just a tiny bubble in something vastly larger, a single island in an endless ocean. And yet, that tiny bubble is more than enough to fill us with wonder. Photons from the CMB have been traveling for over 13 billion years. The light we detect as the cosmic microwave background was released 380,000 years after the Big Bang. But that doesn't mean it's only 380,000 years old. Those photons have been traveling ever since. As the universe expanded, they were stretched and cooled, their wavelength growing longer and longer. Today, they arrive at our telescopes as microwaves, faint and cold, but they've been journeying for over 13 billion years. In that time, the universe has changed dramatically. Stars have formed and died. Galaxies have collided and merged. Planets have come and gone. And through it all, these photons have continued moving, silent messengers from the early universe. When we detect them, we're catching light that began its journey when the cosmos was just a baby. Light that has traveled farther and longer than almost anything else we can observe. And the fact that we can still detect this light, faint as it is a testament to how transparent the universe has become. Once opaque, now clear. Once chaotic, now structured. And the photons keep coming, carrying their ancient story across the expanding void. The Big Bang wasn't silent. We often imagine the early universe as silent, a vast empty void. But in the first few 100,000 years, before atoms formed, the universe was filled with sound. Pressure waves rippled through the hot plasma, oscillations caused by the interplay of gravity and radiation. These weren't sound waves in the way we experience them. There was no air to carry them. But the plasma itself vibrated, compressions and rarefactions moving through the cosmic fluid. These acoustic oscillations left an imprint on the universe, a pattern we can still detect today in the distribution of galaxies and in the CMB. Some scientists have even translated these patterns into sound, creating an audio representation of the early universe's voice. It's a deep, rumbling tone, the echo of vibrations from billions of years ago. So in a sense, the Big Bang had a sound, a cosmic hum resonating through the plasma, shaping the seeds of structure. It's long since faded, but the memory remains, written into the fabric of the universe, waiting to be heard. Dark energy may have been born with the universe. Today, dark energy is the dominant force in the universe, driving its accelerating expansion. But where did it come from? Some theories suggest it was always there, a property of space itself. If that's true, dark energy would have been present from the very beginning, born with the Big Bang. In the early universe, dark energy's effects would have been overwhelmed by the density of matter and radiation. But as the universe expanded and matter spread out, dark energy's influence grew. Today, it makes up about 68% of the universe's total energy, and it's pushing galaxies apart faster and faster. We don't know what dark energy is. It might be the energy of empty space, something called vacuum energy, or the cosmological constant. Or it might be something more dynamic, a field that changes over time. But whatever it is, it seems to be woven into the very fabric of the cosmos, present from the start, patiently waiting for its moment to dominate. And now, billions of years after the Big Bang, dark energy is shaping the universe's fate, driving it toward an ever faster expansion and a cold, distant future. The universe's geometry was determined early. On the shape of space itself, its geometry was largely determined in the first moments after the Big Bang. Is the universe flat, like an infinite sheet, curved inward, like the surface of a sphere, or curved outward, like a saddle? The answer depends on the total density of matter and energy. If the density equals a critical value, space is flat. If it's higher, space curves inward and the universe is closed. If it's lower, space curves outward and the universe is open. Measurements of the CMB and the large-scale structure of galaxies tell us the universe is remarkably flat. Not perfectly flat, but close enough that any curvature is barely detectable. This flatness is another puzzle that inflation helps explain. The exponential expansion stretched space so much that any initial curvature was smoothed out. What we're left with is a universe that appears flat on the largest scales, infinite or nearly so, boundless but not infinite in time. And within this flat geometry, galaxies, stars, and life have emerged, structure arising in the vastness, like islands in a calm, endless sea. Recombination was a mistaken term, the event when electrons and nuclei combine to form atoms. 380,000 years after the Big Bang is called recombination, but it's actually a misnomer. The prefix "re" suggests it happened again, that electrons and nuclei had been combined before, but they hadn't. This was the first time atoms formed. Before this, the universe was too hot for atoms to exist. So why is it called recombination? The term comes from a similar process in laboratory plasmas, where ionized gas cools and electrons recombine with ions. The name stuck in cosmology, even though it's technically incorrect. A more accurate term might be combination or atom formation. But recombination is what everyone uses. It's a small historical quirk, a reminder that scientific language isn't always perfectly logical. Sometimes terms are chosen for convenience or historical reasons, even if they're not quite right. But the event itself is clear. Electrons settled into orbit around nuclei. Atoms formed. The universe became transparent, and the cosmic microwave background was released. Whatever we call it, it was one of the most important moments in cosmic history. The moment the universe opened its eyes. The universe underwent baryogenesis. In the early universe, shortly after the Big Bang, there was a critical event called baryogenesis. This is when more matter, specifically baryons like protons and neutrons, was created than antimatter. Without this imbalance, matter and antimatter would have annihilated each other completely, leaving only energy. But somehow, for reasons we don't fully understand, there was a slight excess of matter. About one extra matter particle for every billion matter-antimatter pairs. That tiny surplus is everything we see today. Physicists believe baryogenesis happened within the first second after the Big Bang, during a period when the universe was cooling rapidly. The exact mechanism is still debated. It likely involves violations of certain symmetries in particle physics, conditions that favor matter over antimatter. The Sakharov conditions, proposed by physicist Andrei Sakharov in 1967, outline what's needed. Baryon number violation, C and CP symmetry violation, and thermal non-equilibrium. All three must be present. We've observed hints of these in particle experiments, but not enough to fully explain the matter-antimatter asymmetry. It remains one of the great unsolved puzzles. Why matter? Why not nothing? The answer, hidden somewhere in the first second of creation, is the reason we exist. The horizon problem was solved by inflation. One of the puzzles that led to the theory of inflation is called the horizon problem. When we look at the cosmic microwave background, we see that it's almost perfectly uniform in temperature. But according to standard Big Bang cosmology, regions on opposite sides of the sky shouldn't have had time to interact and equalize their temperatures. They're separated by distances so vast that light couldn't have traveled between them in the time available. So how did they end up at the same temperature? Inflation solves this. Before inflation, the universe was much smaller, small enough that all regions were in contact and could reach thermal equilibrium. Then, inflation stretched the universe exponentially, pushing these regions far apart. But they retained their uniform temperature because they'd already equalized before being separated. Without inflation, the uniformity of the CMB is a mystery. With inflation, it makes perfect sense. This is one of the main reasons inflation became so widely accepted. It elegantly solves a problem that otherwise seems impossible to explain. The universe's fate may echo its beginning. Some theories suggest the universe's future might mirror its past. Just as it began with a Big Bang, it might end with a big crunch. If the expansion eventually reverses, gravity could pull everything back together, compressing the universe into a hot, dense state once again. Other theories propose a big rip, where accelerating expansion tears everything apart, even atoms, or a big freeze, where expansion continues forever and the universe cools into darkness. Some cyclic models suggest the universe goes through repeated cycles of expansion and contraction, each big crunch followed by a new Big Bang. Each cycle might create a new universe with slightly different physics. We don't know which scenario is correct. Current evidence favors endless expansion, driven by dark energy, but the universe is full of surprises. Its ultimate fate remains an open question, a mystery that extends billions of years into the future. What we do know is that the universe had a beginning, and beginnings often imply endings, or perhaps new beginnings. The story of the Big Bang might not be over. It might be just one chapter in a much longer tale. The CMB was predicted before it was discovered. One of the most remarkable aspects of the Big Bang theory is that it predicted the cosmic microwave background before anyone had seen it. In 1948, physicists Ralph Alpha and Robert Herman calculated that if the universe began in a hot, dense state, there should be leftover radiation from that early heat. They predicted it would have cooled to about 5 Kelvin by now, close to the actual value of 2.7 Kelvin. But at the time, technology wasn't sensitive enough to detect it. Their prediction was largely forgotten. Then, in 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from a radio antenna. They kept detecting a persistent uniform hiss coming from every direction. No matter where they pointed the antenna, the signal remained. They thought it was interference, possibly from pigeon droppings in the antenna. But after cleaning and testing, the signal persisted. Eventually, they learned about the prediction of relic radiation from the Big Bang. They realized they'd found it, the cosmic microwave background. Their discovery earned them the Nobel Prize and confirmed one of the Big Bang theory's key predictions. It was a moment when theory and observation aligned perfectly, a whisper from the early universe, heard at last. Primordial nucleosynthesis lasted only about 3 minutes. The window for creating elements in the Big Bang was remarkably brief. Big Bang nucleosynthesis, the process that forged hydrogen, helium, and traces of lithium, lasted only about 3 minutes. Before this window, around 1 second after the Big Bang, the universe was too hot. Protons and neutrons couldn't stick together. Any nuclei that formed were immediately blasted apart by high-energy photons. After about 3 minutes, the universe had cooled too much. The temperatures and densities weren't high enough for fusion to continue. The window closed. In that brief 3-minute span, about 25% of the universe's mass was converted from hydrogen into helium. Tiny amounts of deuterium, helium-3, and lithium-7 were also created. And that was it. No heavier elements. Those would have to wait for stars. This narrow window is one of the most precisely tested predictions of Big Bang cosmology. When we measure the abundance of these light elements in the universe, they match the theory's predictions almost perfectly. 3 minutes of cosmic chemistry that determined the elemental makeup of the universe for billions of years to come. The universe has no preferred direction. When we look out into space, we don't see any special direction. The universe looks roughly the same in all directions, a property called isotropy. This is closely related to the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. No place is special, and no direction is special. This uniformity is remarkable. It suggests the universe doesn't have a center or an edge, at least not in any observable sense. Everywhere is equivalent. Every observer in any galaxy would see roughly the same large-scale structure. This principle has been tested extensively. The cosmic microwave background is isotropic to better than 1 part in 100,000. Galaxy surveys show large-scale uniformity, and our theories of the Big Bang and cosmic expansion depend on this assumption. Of course, on small scales, the universe is lumpy. Galaxies cluster, voids separate them. But zoom out far enough, and it smooths out. The universe, in the largest view, is a place without preferred positions or directions. A democracy of space, where every point is equal. Quantum mechanics and gravity clash. At the Big Bang, our 2 most successful theories of physics are general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles and forces on the smallest scales. Both theories have been tested extensively and work incredibly well, but they don't work together. And nowhere is this problem more acute than at the Big Bang. In the Planck epoch, the earliest moment after the Big Bang, the universe was so small and so dense that both quantum effects and gravitational effects were important. But we don't have a theory that combines them. General relativity breaks down at singularities. Quantum mechanics doesn't include gravity. Without a theory of quantum gravity, we can't describe what the universe was like at the very beginning. We can only go back to about 10 to the minus 43 seconds after the Big Bang. Before that, we're in the dark. Many physicists are working on this problem. String theory, loop quantum gravity, and other approaches all attempt to unite quantum mechanics and gravity. But so far, none have been confirmed. The Big Bang, in its earliest instant, remains beyond our reach. A moment we can point to, but not yet fully explain. The ultimate frontier of physics, still waiting to be crossed. The universe's age can be calculated from its expansion. One of the remarkable things about the Big Bang theory is that it lets us calculate the age of the universe. By measuring how fast the universe is expanding today, and by understanding how that expansion has changed over time, we can rewind the clock and figure out when everything began. The key measurement is the Hubble constant, which describes the current rate of expansion. Using this, along with data from the cosmic microwave background and distant supernovae, cosmologists have determined that the universe is about 13.8 billion years old. This age is consistent with other independent measurements. The oldest stars we've observed are slightly younger than this. The oldest galaxies we can see formed a few 100 million years after the Big Bang. Everything fits together. The universe began 13.8 billion years ago, and it's been expanding and evolving ever since. It's a precise number, though there's still some uncertainty. Different measurement methods give slightly different values for the Hubble constant, a puzzle called the Hubble tension. But within the margin of error, we know the universe's age with remarkable accuracy. 13.8 billion years. That's how long it's been since the Big Bang lit the spark of creation. The Big Bang theory doesn't explain everything. For all its successes, the Big Bang theory doesn't answer every question. It tells us how the universe evolved from a hot, dense state. But it doesn't explain what caused that state or why the Big Bang happened. It doesn't fully explain the matter-antimatter asymmetry or the nature of dark matter and dark energy. It doesn't tell us what, if anything, came before. These are open questions, frontiers of research. Some may be answered with better observations and new theories. Others may be fundamentally unanswerable, at least with our current understanding of physics. But that's how science works. Theories explain what they can, and they're refined or replaced as we learn more. The Big Bang is our best model of cosmic origins. It's supported by overwhelming evidence, but it's not the final word. It's a work in progress, a story still being written, and that's part of what makes cosmology so exciting. We're not just studying the past, we're actively figuring it out, piece by piece, question by question. The Big Bang is a triumph of human curiosity, and it's far from finished. And there, with this thought gently settling, we reach the midpoint of our journey. We've drifted through the universe's earliest moments, from quantum fluctuations to cosmic inflation, from the first particles to the glow of the CMB. We've felt the heat of creation and watched as it cooled into the cosmos we know today. If you're still awake, if your thoughts are still following along, that's wonderful. But if you've already begun to drift, if your mind is soft and you're breathing slow, that's exactly where you should be. The universe began with a whisper, a quantum trembling that grew into everything. And now, as you rest, that same universe cradles you, made of atoms forged in its first minutes, bathed in the stretched light of its earliest glow. You are part of this story, not separate from it, but woven into its very fabric. So let yourself rest now. Let these facts settle like stardust. And when you're ready, the second half awaits. More mysteries, more wonders, more gentle explorations of the moment when everything began. Sleep well wherever you are. And thank you for traveling back to the beginning with us. Now let's begin. The Big Bang left behind more than light. When we think about what the Big Bang left behind, we usually think of the cosmic microwave background, that ancient light stretched and cooled over billions of years. But the Big Bang left other traces too. Gravitational waves, ripples in space-time itself, should have been produced during inflation. We haven't detected these primordial gravitational waves yet, but experiments are searching. If found, they'd give us a new way to study the earliest moments, before even the CMB was released. The Big Bang also left behind the large-scale structure of the universe. The pattern of galaxies and voids we see today traces directly back to quantum fluctuations in the first fraction of a second, and it left behind the elements, hydrogen, and helium, forged in the first minutes, still make up most of the universe. Every breath you take, every star that burns, carries the signature of those first moments. The Big Bang isn't just history, it's present. Its fingerprints are everywhere, written into the fabric of reality. And the more we look, the more traces we find. The flatness problem challenged early cosmology. Before inflation was proposed, cosmologists faced a puzzle called the flatness problem. For the universe to be as flat as we observe it today, it would have had to be extraordinarily flat in the beginning. Even a tiny deviation from perfect flatness would have been amplified over time. If the early universe was slightly too dense, it would have collapsed back on itself long ago. If it was slightly too sparse, it would have expanded so fast that no structures could form. Yet here we are, in a universe that's remarkably flat. The odds of this happening by chance are vanishingly small. It would be like balancing a pencil on its tip and having it stay upright for billions of years. Inflation solved this problem elegantly. By stretching the universe exponentially, any initial curvature was flattened out, like inflating a balloon until its surface appears flat. After inflation, the universe naturally ended up flat, not by chance, but by process. This is one of inflation's great successes. It turned an improbable coincidence into an expected outcome. A universe that looks fine-tuned but emerged naturally from the physics of the early moments. The universe was once the size of a marble. Try to imagine this. The entire observable universe, everything we can see in any direction, was once compressed into something the size of a marble. Not the matter in it, the space itself, all the volume that now stretches for billions of light years, squeezed into something you could hold in your hand. At that size, the universe was already larger than it had been moments before. During inflation, it had grown from subatomic scales to perhaps marble-sized in less than a trillionth of a second, and it kept expanding from there. By the time the first atoms formed, it had grown much larger still. But there was a moment, brief and strange, when the cosmos was marble-sized, unimaginably dense, impossibly hot, and yet already containing within it the seeds of every galaxy, every star, every world that would ever exist. When you hold something small, a stone or a coin, remember this. The universe was once smaller than what you're holding. Everything from nothing. Vastness from a speck. It's a thought that sits at the edge of comprehension, inviting wonder. Photons dominated the early universe. In the universe's first few 100,000 years, radiation was the dominant form of energy. Photons, particles of light, far outnumbered and outweighed matter particles. This era is called the radiation-dominated epoch. Every cubic centimeter of space was filled with countless photons, bouncing off electrons, interacting constantly with the hot plasma. Matter existed, but it was a minority. The universe was a bright, glowing sea of light. As the universe expanded, this balance shifted. Photons were stretched by expansion, losing energy. Matter particles weren't affected the same way. Eventually, around 50,000 years after the Big Bang, matter overtook radiation as the dominant form of energy. This transition, from radiation-dominated to matter-dominated, changed how the universe evolved. Structure could begin forming. Gravity, acting on matter, could pull things together. Before this transition, radiation pressure kept things smooth. After it, clumping could occur. Today, we live in a matter-dominated universe, though dark energy is now taking over. But in the beginning, it was all about light, a universe glowing from within, bright beyond imagining. The lithium problem remains unsolved. Big Bang nucleosynthesis predicts how much hydrogen, helium, and lithium should have been created in the first few minutes. For hydrogen and helium, the predictions match observations beautifully. But lithium is a problem. Theory predicts about 3 times more lithium-7 than we actually observe in old stars. This discrepancy, called the lithium problem, has puzzled cosmologists for decades. Several explanations have been proposed. Maybe lithium was destroyed in stars more than we thought. Maybe our models of stellar evolution are wrong. Or maybe, just maybe, something about Big Bang nucleosynthesis is incomplete. Some physicists suggest the problem points to new physics, unknown particles or forces that affected the early universe's chemistry. Others think it's just a matter of better understanding how stars process lithium. The mystery remains unsolved. It's a small discrepancy, but in a theory as precise as Big Bang cosmology, small discrepancies matter. They're clues, hints that something deeper is waiting to be understood. And until we solve it, the lithium problem remains a gentle reminder. The universe still has secrets to share. Entropy has been increasing since the Big Bang. The second law of thermodynamics tells us that entropy, a measure of disorder, always increases over time. This has been happening since the Big Bang. The early universe was in a state of high order in some ways, everything compressed, uniform, smooth. But as it expanded and cooled, entropy increased. Particles spread out, energy dispersed, structure formed and then gradually decayed. Stars burn fuel, increasing entropy. Galaxies evolve and age. Black holes absorb matter and radiate away energy. Every process, every change, adds to the universe's total entropy. Some physicists argue that the Big Bang itself was a state of extremely low entropy, and everything since has been a slow slide toward maximum disorder. Eventually, in the far future, the universe may reach a state called heat death. Maximum entropy, no energy gradients, no stars burning, just cold, uniform emptiness. But that's trillions of years away. For now, entropy is still climbing. The universe is still active, still changing. And in that change, in that gradual increase of disorder, life emerged, structure formed, complexity arose. The arrow of time, pointing from the Big Bang to the distant future, is marked by entropy's steady rise. The electroweak epoch lasted less than a trillionth of a second. In the very early universe, around 10 to the minus 12 seconds after the Big Bang, the electromagnetic force and the weak nuclear force were unified. They weren't separate. They were a single force, called the electroweak force. This era is called the electroweak epoch. As the universe cooled, the electroweak force underwent a phase transition and split into 2 distinct forces. Electromagnetism, which governs light and electric charges, and the weak force, which governs radioactive decay. This split was a symmetry breaking, a moment when the universe's laws changed, becoming more complex. Before this, the universe was simpler, governed by fewer forces. After it, we had the 4 forces we know today. This transition is well understood. The theory that describes it, the electroweak theory, has been confirmed by countless experiments. It even earned a Nobel Prize. But the electroweak epoch itself was brief, lasting less than a trillionth of a second. a fleeting moment when the universe's rules were slightly different. Another reminder that the laws of physics aren't fixed and eternal. They emerged, evolved, and settled into the forms we observe today. Neutrinos outnumber atoms by 1 billion to 1. The universe is filled with neutrinos. For every atom in existence, there are roughly 1 billion neutrinos. Most of these come from the Big Bang itself, created in the first second when the universe was hot and dense. These relic neutrinos make up the cosmic neutrino background, similar to the cosmic microwave background, but even harder to detect. Neutrinos are ghostly. They barely interact with anything. Trillions pass through your body every second without leaving a trace. They were created when the universe was about 1 second old, during a period called neutrino decoupling. Before this, neutrinos were constantly interacting with other particles. After this, they drifted freely, streaming through the expanding cosmos. These ancient neutrinos have cooled to just above absolute zero. They're nearly impossible to detect with current technology, but they're there, a vast sea of particles left over from creation. If we could ever detect them directly, they'd give us a window into the universe at 1 second old, earlier than the CMB, closer to the Big Bang itself. For now, they remain invisible, silent witnesses drifting through time. The universe's first structures were tiny. When we think of cosmic structure, we imagine galaxies and clusters, but the first structures to form were much smaller. Dense clumps of dark matter just a few light years across began collapsing under their own gravity shortly after recombination. These mini halos, as they're called, were the seeds of everything larger. Gas fell into these dark matter clumps, drawn by gravity. Over time, the gas became dense and hot enough for the first stars to form. These early stars were massive and short-lived, burning through their fuel in just a few million years. When they exploded, they scattered heavy elements into space, enriching the gas for future generations of stars. The mini-halos themselves merged over time, building larger structures, galaxies, clusters, and eventually the cosmic web. But it all started small, tiny knots of matter, barely held together by gravity, forming in the darkness of the early universe. From these humble beginnings, the grand structures we see today emerged. Layer by layer, merger by merger, the universe building itself, one small step at a time. The photon-to-baryon ratio has been constant. One of the strange constants of the universe is the ratio of photons to baryons, the particles that make up ordinary matter. For every proton or neutron in the universe, there are about 1.6 billion photons. This ratio was set in the first second after the Big Bang, and it's remained constant ever since. As the universe expands, the number of photons stays proportional to the number of baryons. This ratio is important. It affects how the early universe evolved, how much matter could clump together, and what the cosmic microwave background looks like. It's encoded in the CMB's temperature fluctuations. When we measure those fluctuations, we're reading this ratio, and it matches the predictions of Big Bang theory perfectly. Why is the ratio what it is? We don't fully know. It depends on the conditions in the first second, on how particles formed and interacted, but once set, it became a permanent feature of the cosmos, a number written into reality, unchanging. And every photon in the CMB, every particle of light washing over us, is part of that ancient balance. Dark matter doesn't interact with light, One of the defining features of dark matter is that it doesn't interact with light. It doesn't emit, absorb, or reflect photons. It's completely invisible to telescopes. We only know it exists because of its gravitational effects. Dark matter was present in the early universe, helping to shape the first structures. It pulled gas into dense regions where stars could form. It held galaxies together, and it created the cosmic web, the large-scale pattern of matter we see today. But despite its importance, we've never directly detected a dark matter particle. We don't know what it's made of. The most popular candidates are WIMPs, weakly interacting massive particles. But experiments searching for them have come up empty so far. Other possibilities include axions, sterile neutrinos, or something even more exotic. Dark matter is one of the biggest mysteries in cosmology. It makes up about 27% of the universe's total energy. It shaped the cosmos from the beginning, and yet we don't know what it is. It's a humbling reminder. The universe is full of things we can't see, can't touch, but that shape everything we do see. Invisible scaffolding, holding the cosmos together. The universe had a particle horizon. In the early universe, there was a limit to how far light could travel, not because space was limited, but because time was. Light can only travel so far in a given amount of time. This creates something called a particle horizon, the maximum distance from which information could have reached a given point. In the first second after the Big Bang, the particle horizon was tiny. Regions of space that were separated by more than this distance couldn't influence each other. They were causally disconnected. This is related to the horizon problem. How did distant regions of the universe come to have the same temperature if they couldn't communicate? Inflation solves this by proposing that before inflation, the universe was small enough for all regions to be connected. Then inflation stretched them apart. But even today, there's a cosmological horizon. Distant galaxies are receding faster than light can travel through space. We'll never see beyond a certain distance. The universe continues out there, but it's forever beyond our reach. The horizon is still there, just much farther away. A boundary not of space, but of information. Quantum fluctuations were amplified by inflation. During inflation, the universe expanded exponentially, and with it, quantum fluctuations were stretched from subatomic scales to cosmic proportions. These fluctuations, tiny random variations in the energy field driving inflation, became the seeds of all structure. Imagine a quantum jitter, a brief spike in energy density, smaller than an atom. Inflation grabs it and stretches it. In less than a trillionth of a second, that microscopic fluctuation becomes thousands, millions of light years across. When inflation ends, these stretched fluctuations become variations in the density of matter. Slightly denser regions where gravity pulls harder. Over billions of years, those regions collapse into galaxies. So the structure we see today, all the galaxies and clusters, started as quantum noise. Randomness at the smallest scale, amplified to the largest. It's a profound connection. The quantum world, usually confined to atoms and particles, reaching out to shape the cosmos. And it happened because of inflation, a brief violent expansion that turned the invisible into the visible, the microscopic into the cosmic. Baryon acoustic oscillations echo through space. In the early universe before recombination, sound waves rippled through the hot plasma. Pressure waves driven by the interplay of gravity and radiation, created oscillations, regions of compression and rarefaction, moving outward at a significant fraction of the speed of light. When recombination happened and atoms formed, these sound waves froze in place. The matter stopped oscillating, but the pattern remained. Regions that were compressed are now slightly denser. Regions that were rarefied are slightly less dense. This pattern, called baryon acoustic oscillations, is still visible today. We can see it in the distribution of galaxies. Galaxies are slightly more likely to be found at a specific distance from each other, a distance that corresponds to the scale of those ancient sound waves, about 500 million light-years. By measuring this pattern, cosmologists can learn about the early universe's conditions, the density of matter, the strength of dark energy, the expansion rate. Baryon acoustic oscillations are like fossils, patterns from the distant past, preserved in the present, echoes of sound waves that traveled through a universe that no longer exists. The CMB has a dipole anisotropy. When we measure the cosmic microwave background, we find that it's not perfectly uniform. There's a slight temperature difference between one side of the sky and the other. One side is very slightly warmer, the other slightly cooler. This is called the dipole anisotropy. It's not from the Big Bang itself, it's from our motion through space. We're moving relative to the CMB, and that motion creates a Doppler shift. In the direction we're moving, the CMB is blue shifted, appearing slightly warmer. In the opposite direction, it's red shifted, appearing cooler. By measuring this dipole, we can calculate our velocity relative to the CMB. It turns out we're moving at about 370 kilometers per second. That's due to the motion of Earth around the Sun around the galaxy, and the galaxy through space. The dipole tells us something profound. There's a rest frame of the universe, a reference frame defined by the CMB, and we're not in it. We're moving. The universe has a preferred state of rest, even if no location is preferred. It's a subtle reminder. Space isn't just a blank stage. It has properties, structure, and history. The universe underwent rayonization. After recombination, when the first atoms formed, the universe became neutral. Electrons were bound to nuclei, and space was transparent. But it didn't stay neutral. Hundreds of millions of years later, when the first stars ignited, their intense ultraviolet light began ionizing the surrounding hydrogen, stripping electrons away from atoms once again. This process, called reionization, gradually spread through the universe. Each new star, each new galaxy, created a bubble of ionized gas around it. These bubbles grew and merged until eventually nearly all the hydrogen in space was ionized once more. Reionization was complete by about 1 billion years after the Big Bang. Today, most of the universe's hydrogen is still ionized, a thin plasma filling the space between galaxies. Reionization marks the end of the Dark Ages and the beginning of the cosmic dawn, the era when light returned to the universe. And it's a reminder that cosmic history isn't linear. The universe became transparent, then partly opaque again, then transparent in a different way. A story of cycles and transitions, each shaping the cosmos in new ways. The speed of light was the ultimate speed limit from the start. From the moment the Big Bang occurred, the speed of light was the universe's ultimate speed limit. Nothing with mass can reach it. No information can travel faster than it. This isn't just a rule for light. It's a fundamental property of space-time itself. In the early universe, when everything was hot and dense, particles moved at speeds close to light speed, but never beyond it. Even during inflation, when space itself expanded faster than light, no object moved through space faster than light. The expansion was of space, not in space. This speed limit has profound consequences. It means causality is preserved. Effects can't precede causes. It means distant events take time to influence us. And it means the observable universe has a boundary. We can only see as far as light has traveled since the Big Bang. The speed of light, constant and unchanging, has shaped the universe's structure and our ability to observe it. It's woven into the fabric of reality, a law that emerged with the Big Bang and has governed everything since, fast but finite, a limit that defines what's possible. Gravitational waves stretch and squeeze. Space-time, during the Big Bang, particularly during inflation, gravitational waves should have been produced. These are ripples in space-time itself, traveling at the speed of light. Unlike electromagnetic waves, which are oscillations of fields, gravitational waves are oscillations of the fabric of space. As a gravitational wave passes, it stretches space in one direction and squeezes it in another, then reverses. The effect is tiny, but detectable with sensitive instruments. We've detected gravitational waves from colliding black holes and neutron stars, but we haven't yet detected primordial gravitational waves from the Big Bang. If we could, they'd be incredibly valuable. They'd carry information from the inflationary epoch before the CMB was released. They'd let us probe the universe at an even earlier moment. Experiments are searching for these waves. They look for subtle patterns in the CMB, specific polarization signals that gravitational waves would create. It's challenging. The signals are faint, buried in noise. But if found, primordial gravitational waves would be a direct signature of inflation, a smoking gun, proof that the universe underwent exponential expansion in its first moments, and a new window into the deepest mysteries of cosmic origins. The universe is isotropic and homogeneous on large scales. When we look at the universe on the largest scales, we see something remarkable. It looks the same in all directions, a property called isotropy, and it looks the same everywhere, a property called homogeneity. This is the cosmological principle, the assumption that the universe is uniform on large scales. It's not exact. On small scales, there are galaxies, clusters, and voids, lots of structure. But zoom out far enough, and it smooths out, like looking at a pointillist painting. Up close, it's dots. From a distance, it's a uniform image. The cosmological principle is a foundational assumption of Big Bang cosmology. It lets us treat the universe as a whole, using the same laws of physics everywhere, and observations support it. The CMB is uniform. Galaxy surveys show large-scale homogeneity. There's no preferred location or direction. This uniformity is a clue. It suggests the universe began in a smooth state and evolved in a symmetric way. Inflation explains how it became so uniform. And the structures we see today grew from tiny fluctuations in that smooth background. Order from uniformity, complexity from simplicity. The particle physics standard model emerged from the Big Bang. The standard model of particle physics, the theory that describes all known particles and 3 of the 4 forces, has its roots in the Big Bang. As the universe cooled, particles and forces emerged in stages. First, the unified force split into gravity and the others. Then the strong force separated. Then the electromagnetic and weak forces divided. Each splitting created new particles and interactions. Quarks, leptons, bosons all appeared as the universe reached the right temperatures. The Higgs boson, discovered in 2012, is part of this story. It's associated with the field that gives particles mass. And that field underwent a phase transition in the early universe, around 10 to the minus 12 seconds after the Big Bang. Before the Higgs transition, particles were massless. After it, they acquired mass. This changed everything. Massive particles move slower than light. They can bind together. They can form structures. Without the Higgs field and its transition, the universe would be very different. The Standard Model, tested and confirmed in countless experiments, is a map of the universe's early moments, a guide to how matter and forces came to be. The CMB is nearly a perfect black body. When we measure the spectrum of the cosmic microwave background, we find something remarkable. It's almost a perfect black body spectrum. A black body is an idealized object that absorbs and emits radiation perfectly, with a characteristic curve that depends only on temperature. The CMB follows this curve to incredible precision. It's the most perfect black body ever observed. This tells us something important. The early universe, when the CMB was released, was in thermal equilibrium. Everything was at the same temperature. Particles were interacting constantly, exchanging energy, smoothing out any variations. When recombination happened and the universe became transparent, this thermal equilibrium was frozen in. The photons we detect today still carry that perfect distribution. The CMB's black body spectrum is a signature of the Big Bang. It's exactly what we'd expect from a hot, dense, uniform early universe. Any alternative theory of cosmic origins would have a hard time explaining it. It's one of the pillars of Big Bang cosmology, a simple observation that speaks volumes. The universe was once in perfect balance, and the light from that moment still glows pure and unchanged. Cosmic strings might exist as relics. During phase transitions in the early universe, when forces separated and symmetries broke, defects might have formed in spacetime. One type of defect is called a cosmic string. These are thin, incredibly dense filaments of energy stretched across space. If they exist, cosmic strings would be relics from the universe's first moments, thinner than an atom, but with immense mass. A cosmic string just 1 meter long would weigh as much as Earth. These strings would warp space-time around them, creating gravitational effects. They might seed the formation of galaxies. They might produce gravitational waves, and they might leave subtle imprints in the cosmic microwave background. Searches have been conducted, but no cosmic strings have been found yet. It's possible they don't exist. Not all phase transitions produce defects. Or maybe they're so rare that we haven't seen one. Or maybe they decayed away over billions of years. But the idea remains intriguing. Cosmic strings would be fossils from the Big Bang, direct evidence of the universe's earliest phase transitions. And if found, they'd open a new window into the conditions that shape reality. For now, they're hypothetical, but the universe has surprised us before. The universe's critical density determines its fate. There's a special value called the critical density. It's the amount of matter and energy the universe needs to be geometrically flat. If the actual density is higher than critical, the universe is closed and will eventually collapse. If it's lower, the universe is open and will expand forever. If it's exactly critical, the universe is flat and will expand forever, gradually slowing but never stopping. Measurements of the CMB and large-scale structure tell us the universe is very close to critical density, so close that it's essentially flat. This is another puzzle inflation solves. By stretching the universe so much, inflation drove the density toward the critical value. But here's the interesting part. When we add up all the matter, ordinary and dark, we only get about 30% of critical density. The rest, about 70%, comes from dark energy. Together, matter and dark energy bring the universe to critical density. This balance determines the universe's fate. With dark energy dominating, the expansion is accelerating. The universe will expand forever, faster and faster. Galaxies will drift apart, stars will burn out, and in the far future, the cosmos will be cold, dark, and empty. But that's trillions of years away. For now, we're in a brief era when structure still exists, stars still shine, and the universe is full of light. Vacuum energy may have driven inflation. What caused inflation? What force drove the universe to expand exponentially in its first fraction of a second? The most popular idea is a field called the inflaton, a hypothetical field that filled space, carrying enormous energy. As this field rolled toward its minimum energy state, it released energy, driving exponential expansion. When the field reached its minimum, inflation ended. The energy was converted into particles and radiation, reheating the universe. This is the general picture, but the details are unclear. We don't know what the inflaton is. We don't know its properties or how it interacts with other fields. Some theories suggest it's related to the Higgs field. Others propose entirely new physics. And there's another idea. Vacuum energy, the energy of empty space itself. In quantum mechanics, even empty space has energy, fluctuations that pop in and out of existence. If vacuum energy was high in the early universe, it could have driven inflation. Then it dropped to a lower value and normal expansion took over. This is speculative. We don't have direct evidence for the inflaton or high vacuum energy. But something drove inflation. Some field, some force, some property of the early universe. And finding it is one of the great quests of modern cosmology. Redshift tells us how much the universe has expanded. When we observe distant galaxies, we see that their light is redshifted. The wavelengths are stretched, shifted toward the red end of the spectrum. This happens because the universe is expanding. As light travels through space, space itself stretches, and the light stretches with it. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with a redshift of 1 means the universe has doubled in size since its light left. A redshift of 2 means it's tripled. The cosmic microwave background has a redshift of about 1100. The universe has expanded by a factor of 1100 since the CMB was released. What was once visible light is now microwaves. Redshift is one of our most powerful tools. It lets us measure distances, determine the universe's expansion rate, and study how the cosmos has evolved. Every observation, every spectrum, carries information about expansion. And all of it traces back to the Big Bang, a single event that set the universe in motion, stretching space, shifting light, and creating the dynamic cosmos we observe today. The Big Bang was not a singular point. Despite what the name suggests, the Big Bang wasn't a single point in space where everything exploded outward. It was everywhere, all at once. The entire universe was compressed, not into a point in space, but into a state where space itself was tiny. Every location, every region was part of the Big Bang. There's no center, no place where it happened more than anywhere else. This is hard to visualize. We're used to thinking of explosions as happening at a location. But the Big Bang wasn't an explosion in space. It was an explosion of space. And everywhere you look, in every direction, you're seeing the aftermath. The galaxies receding from us, the cosmic microwave background glowing faintly, the expansion continuing. All of it is the Big Bang, still happening in a sense. When you ask where the Big Bang occurred, the answer is here, and there, and everywhere. Every point in space was once the same point, and as space expanded, those points separated, becoming the vast cosmos we see today. The Big Bang is not a place. It's an event, a process, and we're still living in its wake. The Sachs-Wolf effect links CMB to large-scale structure. The cosmic microwave background has tiny temperature variations, patterns that tell us about the early universe. One source of these variations is the Sachs-Wolf effect. Photons climbing out of gravitational wells lose energy, becoming slightly cooler. Photons falling into wells gain energy, becoming slightly warmer. In the early universe, regions with slightly higher density had stronger gravity. Photons leaving these regions lost more energy. On the CMB, these regions appear as cool spots. Regions with lower density appear as warm spots. This effect links the CMB to the large-scale structure we see today. The pattern of hot and cold spots in the CMB matches the distribution of galaxies billions of years later. The same overdensities that created cool spots in the CMB became the seeds of galaxy clusters. The same underdensities that created warm spots became cosmic voids. The Sachs-Wolf effect is a bridge, a connection between the universe at 380,000 years old and the universe today. It shows that structure grew from tiny initial fluctuations, and it gives us a way to test our models, comparing predictions to observations. Theory and reality aligned. Nucleosynthesis ended when the universe cooled below fusion temperatures. Big Bang nucleosynthesis, the creation of light elements, ended not because time ran out, but because the universe cooled below the temperature needed for fusion. Around 3 minutes after the Big Bang, the temperature dropped to about 100 million Kelvin. Still incredibly hot, but not hot enough for protons and neutrons to overcome their electrical repulsion and fuse. Fusion stopped. The ratio of elements was locked in. About 75% hydrogen, 25% helium, and trace amounts of deuterium and lithium. This is why stars exist. Stars recreate the conditions of the early universe. In their cores, temperatures reach millions of degrees, hot enough for fusion to resume. Hydrogen fuses into helium. Helium fuses into carbon and oxygen, and so on, up to iron. But the Big Bang couldn't make heavy elements. The window was too brief. The temperatures too low by the time the right conditions existed. Heavy elements had to wait for stars, and when those stars died, they scattered their creations into space, enriching the universe, seeding planets and life. But the foundations, hydrogen and helium, came from the Big Bang. The raw materials forged in the first 3 minutes. The cosmological constant may be the simplest explanation for dark energy. Dark energy, the mysterious force accelerating the universe's expansion, might be the energy of empty space itself. This is called the cosmological constant. Einstein introduced the cosmological constant in 1917 as a fudge factor to keep the universe static, which was believed at the time. When Hubble discovered the universe was expanding, Einstein called it his greatest blunder. But the constant came back. In the 1990s, observations of distant supernovae showed the expansion was accelerating. Something was pushing space apart. The simplest explanation is the cosmological constant, a constant energy density filling all of space. As the universe expands, more space is created, and with it, more dark energy. This drives acceleration. The problem is the value. Quantum field theory predicts a vacuum energy 120 orders of magnitude larger than observed. It's one of the worst predictions in physics. So either our understanding of quantum fields is wrong, or something cancels out most of the vacuum energy, leaving just a tiny residual. This is the cosmological constant problem. Unsolved, but important. Whatever dark energy is, it's shaping the universe's fate. And it might have been there, quietly, since the Big Bang. The first stars were massive and metal-free. The very first stars to ignite in the universe, known as population 3 stars, were different from any stars we see today. They formed from pure hydrogen and helium, with no heavier elements, no metals in astronomers' terms. Without metals, the gas couldn't cool efficiently. It stayed hot, and only very large clumps could collapse under gravity. This meant the first stars were massive, perhaps 100 times the mass of the Sun or more. These giants burned hot and bright. Their lifetimes were short, just a few million years, and when they died, they exploded as supernovae, scattering the first heavy elements into space. These elements, carbon, oxygen, silicon, iron, enriched the surrounding gas. Later generations of stars formed from this enriched material. Over billions of years, the universe's chemical composition changed. More metals, less pure hydrogen and helium. Today, stars like the Sun are metal-rich compared to the early universe. We haven't directly observed a population 3 star yet. They're too distant, too faint. But we see their influence. The metals they created, the galaxies they helped form. The first stars lit up the universe and set the stage for everything that followed. Time dilation affects the observed universe. One of the effects of the universe's expansion is time dilation. Events in the distant past appear to unfold more slowly when we observe them. This is because the light we're seeing was stretched by expansion. A supernova that took 20 days to fade in its own reference frame appears to take 40 days if it's at a redshift of 1. The explosion happened at the same rate, but we see it slowed down because the universe expanded while the light traveled. This time, dilation is observable. Astronomers have confirmed it by studying distant supernovae and gamma-ray bursts. The higher the redshift, the slower events appear. It's a direct consequence of expansion, predicted by relativity and confirmed by observation. This means when we look at the early universe, we're not just looking at distant objects. We're seeing events that unfolded in slow motion, stretched by billions of years of cosmic expansion. Time itself, woven into the fabric of space, bears the mark of the Big Bang. The abundance of deuterium constrains cosmic conditions. Deuterium, heavy hydrogen with 1 proton and 1 neutron, is a sensitive probe of the early universe. Unlike regular hydrogen and helium, which were produced in large amounts, deuterium was created in tiny quantities, and it's easily destroyed in stars. This makes primordial deuterium special. The amount created in the Big Bang depends on the density of ordinary matter. Higher density means more collisions, more reactions, and less deuterium survives. Lower density means less destruction, more deuterium remains. By measuring deuterium in pristine gas clouds, clouds that haven't been processed by stars, we can determine the density of ordinary matter in the early universe, and the measurements match Big Bang predictions beautifully. The deuterium abundance tells us that ordinary matter, protons and neutrons, makes up about 5% of the universe's total energy. The rest is dark matter and dark energy. Deuterium is a cosmic fossil, a fragile remnant from the first few minutes preserved in the space between galaxies, and its abundance is a window into conditions we can't directly observe. Chemistry as archaeology, atoms as evidence of the distant past. The CMB polarization contains hidden information. The cosmic microwave background isn't just a map of temperature, it's also polarized. Light waves oscillate, and polarization describes the direction of that oscillation. The CMB has two types of polarization, called E modes and B modes. E modes come from density fluctuations. They're caused by the same overdensities that create temperature variations. We've measured them extensively. B modes are different. They can be created by gravitational waves from inflation. Detecting primordial B modes would be direct evidence of inflation, proof that the universe underwent exponential expansion. Several experiments have searched for B modes. They're challenging to detect because they're faint and easily confused with foreground signals from our galaxy. In 2014, one experiment claimed a detection, but it turned out to be dust. The search continues. If primordial B modes are found, it will be a landmark discovery, direct evidence of inflation, a window into the universe at 10 to the minus 35 seconds after the Big Bang, and confirmation of one of the most important ideas in modern cosmology. The CMB still has secrets, and we're learning to read its subtle signals, one polarization pattern at a time. The cosmic microwave background has traveled farther than any object we can see. When we observe the cosmic microwave background, we're detecting photons that have been traveling for over 13 billion years. But here's something remarkable, something that seems to defy logic at first. The place where those photons were emitted is now much farther away than 13 billion light years. Much farther. This seems impossible at first. If light has been traveling for 13 billion years, shouldn't the source be 13 billion light years away? It's a reasonable assumption. Light travels at a fixed speed, so distance equals speed times time. Simple mathematics. But the universe doesn't play by simple rules. The universe has been expanding while the light traveled. And not just expanding, but expanding in a way that affects everything we observe. The region that emitted the CMB photons we detect today, that glowing surface from 380,000 years after the Big Bang, has been carried away by expansion. It's now about 46 billion light years away, nearly 3 times farther than the light travel time would suggest. Even though the light has only been traveling for 13.8 billion years, the source has moved dramatically farther in that time. This is why the observable universe is about 93 billion light years across, not 27.6 billion. If we simply multiplied the age of the universe by the speed of light and doubled it, we'd get a much smaller number. but space itself has been stretching the whole time. Every moment, every second, every year that these photons have been traveling, the space between their origin and us has been expanding. It's like running on a treadmill that's accelerating. You cover a certain distance with your steps, but the treadmill itself is moving, carrying you backward even as you run forward. Except, in the universe's case, it's space itself that's moving, stretching, creating more distance between any 2 points. The CMB photons we see today left from a surface 380,000 years after the Big Bang, a spherical shell surrounding us in all directions. But that surface has moved away dramatically since then. It's been carried by expansion to distances we can calculate but barely comprehend. We'll never see it as it is now. We can only see how it was, frozen in that ancient moment when the universe became transparent, a snapshot from the past, preserved in light, traveling toward us through expanding space. And every day, as expansion continues, that surface recedes a little farther, carried by the stretching of space itself, a horizon that moves away faster than we can chase it. If we could somehow travel toward the source of the CMB at nearly the speed of light, we'd never reach it. Not because we're not fast enough, but because space is expanding faster than we can cross it. The destination is retreating faster than we can approach. It's a cosmic race we can never win. A boundary defined not by distance alone, but by the nature of space-time itself. This creates a strange situation. The farthest objects we can see, the sources of the most ancient light, are also the objects that have moved farthest away. They're unreachable, not because of distance, but because of expansion. And this expansion continues, relentless and accelerating. In the far future, distant galaxies will cross this horizon. Their light will no longer reach us. The observable universe will shrink in content if not in size. We live in a privileged time, a time when we can still see deep into the past, far across space. But that privilege is temporary. The universe is slowly pulling its secrets farther away, one by one. And the CMB, that most ancient light, will remain visible, but will tell of an ever more distant past. The antimatter asymmetry may point to new physics beyond the standard model. The fact that matter survived and antimatter didn't remains one of physics' deepest mysteries. It's a puzzle that has haunted cosmologists and particle physicists for decades. Every experiment we've done, every observation we've made, confirms that matter and antimatter should have been created in equal amounts in the Big Bang. And when they meet, they annihilate perfectly. 1 + 1 = 0. Nothing but energy remains. So why is there something instead of nothing? Why are we here? Why is there a universe full of matter, of stars and planets and people, instead of just empty space filled with radiation? The standard model of particle physics can't fully explain it. There are processes that violate the necessary symmetries, small asymmetries in how particles decay. We've observed these in experiments with strange particles called kaons and B mesons. They decay differently depending on whether they're matter or antimatter. But the effect is tiny, far too small to account for the observed imbalance. If the standard model were the whole story, the asymmetry it predicts would leave us with a universe that's almost entirely empty. One matter particle for every trillion, not one for every billion. The numbers don't add up. This suggests something beyond the standard model must have been at work in the early universe. Some additional mechanism, some new physics that we haven't discovered yet. Perhaps new particles that haven't been detected in our accelerators. Particles that only existed at the extreme energies of the first moments after the Big Bang. Perhaps new forces that only operated at those temperatures. Forces that have since become so weak or short-ranged that we can't observe them in modern experiments. Or perhaps additional dimensions of space that influenced how particles behaved. Dimensions that are now curled up so tightly that they're invisible to us. Some theories propose that neutrinos played a role. Neutrinos are strange particles. They barely interact with anything. They come in 3 types or flavors, and they might have properties we don't fully understand yet. If neutrinos are their own antiparticles, a property called being Majorana fermions, they might have created the asymmetry through a process called leptogenesis. The idea is that in the early universe, there were heavy neutrinos, much heavier than the ones we know today. These heavy neutrinos would have decayed asymmetrically, producing slightly more leptons, particles like electrons, than antileptons. This lepton asymmetry would then have been converted into the baryon asymmetry we observe through a process that respects the laws of physics, but allows the conversion. Other theories invoke grand unified theories, frameworks that attempt to unify the strong, weak, and electromagnetic forces into a single force. In these theories, at very high energies, all 3 forces become one, and in that unified state, new processes become possible. Processes that can create more matter than antimatter. When the universe cooled and the forces separated, this asymmetry was locked in, frozen into the structure of reality. Some theories also propose supersymmetry, a symmetry between matter particles and force-carrying particles. If supersymmetry exists, and if it was broken in the right way in the early universe, it could have created the matter-antimatter imbalance. There are even connections to dark matter. Some models suggest that the same process that created the matter asymmetry also created dark matter. That dark matter is somehow a partner or remnant of the baryogenesis process. If this is true, studying dark matter might give us clues about why matter won out over antimatter. The antimatter mystery is a window, a crack in our understanding that suggests deeper truths waiting beneath. Whatever solved it happened in the universe's first second, at energies we can't yet recreate in laboratories. Energies that dwarf anything achievable with current particle accelerators. The Large Hadron Collider, the most powerful accelerator ever built, can't come close to the conditions of the first microsecond. But the evidence is everywhere. Every atom, every star, every living thing exists because of that ancient imbalance. We are the descendants of a cosmic accident, or perhaps a cosmic necessity. A universe that chose matter over antimatter for reasons we don't yet fully grasp. And understanding why remains one of the most important questions in fundamental physics. It's not just about the past. It's about the nature of physical law, about whether the universe had to be this way, or if it was contingent, accidental, about whether there are deeper principles governing reality that we haven't discovered yet. The answer is written somewhere in the mathematics of particle physics, in the behavior of quantum fields at extreme energies. And when we find it, when we finally understand why matter exists, we'll have uncovered one of the universe's most profound secrets. A secret that determines why there is something rather than nothing. The Planck satellite mapped the CMB with unprecedented precision. In 2009, the European Space Agency launched the Planck satellite, a mission designed to map the cosmic microwave background with exquisite precision. It wasn't the first mission to study the CMB. Earlier satellites like COBE and WMAP had already provided remarkable data, but Planck was different. It was more sensitive, more precise, more capable than anything that had come before. For 4 years, it scanned the entire sky, measuring the CMB's temperature and polarization in 9 different frequencies. Each measurement was calibrated to incredible accuracy. Each pixel in its maps represented a tiny patch of the ancient universe, captured in unprecedented detail. The result was the most detailed map of the early universe ever created, a portrait of the cosmos at 380,000 years old, rendered in false color, showing temperature variations of just a few millionths of a degree. Hot spots and cold spots, patterns and structures, the fingerprints of quantum fluctuations stretched by inflation and amplified by billions of years of cosmic evolution. When scientists first saw the full sky map, they were looking at the baby picture of the universe, the oldest snapshot in existence, and it was beautiful. Planck's measurements confirmed many predictions of Big Bang cosmology with stunning accuracy. The age of the universe, 13.8 billion years, plus or minus a few tens of millions, a precision that would have seemed impossible just a few decades earlier. The amount of ordinary matter, the protons and neutrons that make up atoms, 4.9% of the universe's total energy, dark matter, the invisible scaffolding that holds galaxies together, 26.8%, dark energy, the mysterious force accelerating expansion, 68.3%. These numbers are now cornerstones of cosmology. They define the universe's composition, its history, its fate. The data was so precise that cosmologists could test theories with unprecedented rigor. Models that seemed reasonable before Planck were ruled out by the data. Predictions that matched observations to within error bars became strongly confirmed. The standard model of cosmology, the Lambda CDM model, passed every test. It fit the data almost perfectly. Every peak and valley in the CMB's power spectrum, every correlation in the temperature map, everything matched the predictions. Planck also measured the CMB's temperature fluctuations to better than 1 part in a million. It detected subtle patterns that reveal how the universe evolved. The scale of acoustic oscillations, the sound waves that rippled through the early plasma, the effects of gravitational lensing, where the CMB light was bent by massive structures between us and the surface of last scattering. The contributions of different types of matter and energy, each leaving its own subtle imprint on the pattern. By analyzing these signatures, scientists could tease apart the universe's composition and history in extraordinary detail. The mission ended in 2013, but the data continues to be analyzed. Each paper reveals new details, new constraints, new insights into cosmic history. Scientists have extracted information about neutrinos, about the sum of neutrino masses, about the number of neutrino species, about the possibility of exotic particles or fields in the early universe, about the nature of dark energy and whether it changes over time. Every subtle feature in the data is a clue, and teams around the world are still finding new ways to read those clues. Planck also searched for signatures of cosmic inflation, specifically for B-mode polarization in the CMB that would indicate primordial gravitational waves. These waves, if detected, would be direct evidence of inflation, a smoking gun. Planck set strong limits on their amplitude, showing that if they exist, they're weaker than some models predicted. The search continues with other experiments, but Planck narrowed down the possibilities significantly. The satellite showed us the baby picture of the universe in stunning clarity, a portrait captured with a precision that generations of scientists had worked toward, and that image has become the foundation for modern cosmology, a reference point against which all theories must be tested. Every model of the early universe, every proposal about dark matter or dark energy must explain Planck's observations, must fit the patterns in that ancient light. It's a standard so high, so precise, that meeting it is a triumph. And Planck set that standard, a mission that changed cosmology forever. The universe's curvature is constrained to be nearly flat. One of the most important measurements in cosmology is the curvature of space, the shape of the universe itself. Is the universe flat, like an infinite sheet extending in all directions? Positively curved like the surface of a sphere, where if you travel far enough in one direction, you eventually come back to where you started? Or negatively curved, like a saddle, where parallel lines diverge and angles in triangles add up to less than 180 degrees? The answer affects everything. How the universe will evolve, whether it's finite or infinite, what the geometry of space-time looks like on the larger scales. Observations, particularly of the cosmic microwave background, have constrained the curvature to be incredibly close to flat. The parameter that describes curvature is called omega k. If it's 0, the universe is flat. If it's positive, the universe is open, negatively curved. If it's negative, the universe is closed, positively curved. Planck and other experiments have measured omega k to be consistent with 0 within a small margin of error, less than 0.005 in magnitude. Some analyses put the constraint even tighter, less than 0.01. This means if there's any curvature at all, it's so slight that it's undetectable over the observable universe. You could travel billions of light years in any direction, and the geometry would still look flat. Space behaves like Euclidean space, the familiar geometry you learned in school. Parallel lines stay parallel. Angles in triangles add up to 180 degrees. The circumference of a circle is exactly 2p times its radius. Why is the universe so flat? This was a major puzzle before inflation was proposed. Without inflation, this would be an incredible coincidence. The density of the universe would have had to be fine-tuned to extraordinary precision in the first moments. 1 part in 10 no 60 or more. Even a tiny deviation from perfect flatness would have been amplified over time. If the early universe were slightly too dense, just a fraction of a percent too much matter, it would have collapsed back on itself long ago in a big crunch. If it was slightly too sparse, slightly too little matter, it would have expanded so fast that no structures could form, no galaxies, no stars, no planets, just a thin diffuse gas spreading through an empty void. Yet here we are, in a universe that's remarkably flat. The odds of this happening by chance are vanishingly small. It would be like balancing a pencil on its tip and having it stay upright for billions of years. Possible in principle, but so improbable that it demands an explanation. You wouldn't believe someone who said it just happened. You'd look for a mechanism, some force or constraint that made it happen. Inflation solved this problem elegantly by stretching the universe exponentially in its first fraction of a second. Any initial curvature was flattened out, like inflating a balloon to enormous size. When a balloon is small, its surface is obviously curved, but blow it up to the size of Earth or larger, and any small patch of its surface looks flat. The curvature is still there mathematically, but it's so gentle, spread over such a large area, that locally it's undetectable. Inflation did this to space itself. Whatever curvature existed initially was stretched to cosmic scales, leaving the observable universe essentially flat. After inflation, the universe naturally ended up flat, not by chance but by process. Not because conditions were fine-tuned, but because inflation flattened everything. This is one of inflation's great successes. It turned an improbable coincidence into an expected outcome. A universe that looks fine-tuned emerged naturally from the physics of the early moments. This flatness has profound implications. If the universe is exactly flat, which many theories suggest, and which observations support within error bars, then it's likely infinite in extent. There's no edge, no boundary, just endless space extending in all directions. Every galaxy we see is just one among infinite galaxies spread across infinite space, and every region, no matter how distant, is governed by the same laws of physics, shaped by the same Big Bang. If the universe is closed, positively curved, it could be finite but unbounded. Like the surface of a sphere, you could travel in a straight line forever and eventually return to your starting point without ever hitting an edge. But current observations strongly disfavor this. The universe appears too flat to close back on itself, at least within the observable region. A cosmos without center, without border, uniform and vast beyond comprehension. Every point equivalent to every other point. No special locations, no preferred directions. Just an endless expanse of space, flat on the largest scales, filled with galaxies and structure shaped by gravity and time. And all of it emerging from a beginning. A Big Bang that happened everywhere at once, creating this vast, flat, seemingly infinite reality we inhabit. Primordial black holes might have formed in the early universe. Not all black holes come from collapsing stars. Some might have formed in the very early universe, born directly from the conditions moments after the Big Bang. These are called primordial black holes, and they'd be fundamentally different from the stellar black holes we observe today. Stellar black holes form when massive stars exhaust their fuel and collapse under their own gravity. But primordial black holes would have formed from density fluctuations in the first fraction of a second, when the universe was still incredibly hot and dense. Here's how it would work. During the early universe, there were fluctuations in density, quantum jitters stretched by inflation into macroscopic variations. Most of these were small, just slight overdensities that would eventually become galaxies. But if any region was dense enough, if the fluctuation was strong enough, it could collapse directly into a black hole before the universe expanded and cooled. No star needed, no nuclear fusion, just gravity overwhelming the pressure and creating an event horizon. Primordial black holes could have any mass. Some might be tiny, smaller than atoms, with masses comparable to asteroids or mountains. these would have formed from the smallest, densest fluctuations. Others might be massive, thousands or even millions of times the Sun's mass. These would come from larger scale overdensities in the primordial plasma. There's no natural mass scale like there is for stars, where the processes of stellar evolution determine typical masses. Primordial black holes are limited only by the spectrum of density fluctuations in the early universe. If primordial black holes exist, they could explain some cosmic mysteries. One of the biggest is dark matter. We know dark matter exists because of its gravitational effects, but we don't know what it's made of. Most theories assume it's particles, WIMPs or axions, or something exotic. But what if some or all of dark matter is actually primordial black holes? They're massive. They don't emit light. They interact only through gravity. They fit the profile perfectly. There are constraints though. If primordial black holes make up all of dark matter, they'd have effects we should observe. Very small black holes would have evaporated by now through Hawking radiation, so we can rule out certain mass ranges. Large black holes would cause gravitational lensing, brightening background stars when they pass in front, and surveys have constrained how many can exist. But there's a window, roughly between the mass of an asteroid and a few tens of solar masses, where primordial black holes could still make up a significant fraction of dark matter. Primordial black holes might also seed the formation of the first galaxies. In the early universe, before the first stars formed, these black holes would have been gravitational wells. Gas would fall into them, heating up and radiating. This radiation could influence the surrounding matter, helping it collapse into the first protogalaxies. The supermassive black holes we find at the centers of galaxies, millions or billions of times the Sun's mass, might have grown from primordial seeds. These black holes seem too large to have grown from stellar remnants in the time available, but if they started as massive primordial black holes, they'd have a head start. Searches for primordial black holes are ongoing. Gravitational wave detectors like LIGO and Virgo have found black hole mergers with unexpected properties. Some of the black holes are heavier than we'd expect from stellar evolution, in a range called the pair instability gap, where stars shouldn't form black holes. These might be primordial, or they might be stellar black holes that formed in unusual ways. The data is still ambiguous. Gravitational microlensing offers another way to find them. When a massive object passes between us and a distant star, it bends the star's light, causing it to brighten briefly. Surveys monitor millions of stars looking for these events. They found several, but attributing them to primordial black holes requires ruling out other possibilities. Brown dwarfs, free-floating planets, ordinary black holes, all can cause similar signals, but so far evidence is limited. We know stellar black holes exist. Dozens have been confirmed through X-ray observations of binary systems and gravitational wave detections. We know supermassive black holes exist. Nearly every large galaxy has one at its center. But primordial black holes remain hypothetical. Possible relics from the Big Bang, hiding in the darkness, waiting to be discovered. If they're out there, they're fossils from the universe's first moments. Direct descendants of quantum fluctuations, amplified by inflation, collapsed into gravity's ultimate form. Black holes not from death, but from birth. Not from the end of a star's life, but from the beginning of everything. and finding them would be a profound discovery. Evidence that the early universe was more dynamic, more violent, more varied than we imagined. A window into conditions we can barely study otherwise. For now, they remain a possibility. A mystery waiting at the intersection of cosmology, gravity, and quantum physics. The Hubble tension suggests something is missing in our understanding. When cosmologists measure the universe's expansion rate, the Hubble constant, they get different answers depending on how they measure it. It's one of the most fundamental numbers in cosmology. It tells us how fast the universe is expanding today, how quickly galaxies are moving away from each other, and it's connected to the age of the universe, its composition, and its future. But there's a problem. Two different methods give two different answers, and the disagreement has only grown stronger as measurements have improved. Observations of the early universe using the cosmic microwave background give one value. Planck's data, combined with models of how the universe evolved, predicts a Hubble constant of about 67 kilometers per second per megaparsec. This means for every megaparsec of distance, about 3.26 million light-years, galaxies are moving away 67 kilometers per second faster. It's a prediction based on the early universe's conditions, extrapolated forward using our best models. Observations of the nearby universe using direct distance measurements to galaxies give another value. Astronomers use what's called the cosmic distance ladder, a series of methods that build on each other. They measure distances to nearby stars using parallax. They use those stars to calibrate the brightness of certain variable stars called Cepheids. They use Cepheids to calibrate the brightness of type Ia supernovae, stellar explosions that can be seen across the cosmos. And with those calibrations, they measure distances to galaxies and determine how fast they're receding. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. The difference is small in percentage terms, about 9%. But it's persistent, and it's statistically significant. Multiple teams using different methods and different data sets get consistent results within each approach. The early universe measurements cluster around 67. The late universe measurements cluster around 73. The error bars don't overlap. Something is wrong. This discrepancy is called the Hubble tension, and it's become one of the hottest topics in cosmology. At first, scientists thought it might be due to measurement errors. Perhaps something about how we calibrate Cepheid distances is off. Perhaps there are systematic errors in the parallax measurements, or in how we interpret supernova brightness, or perhaps the way we model the CMB's implications is incomplete. But as measurements have improved, the tension has persisted. Both methods have been checked and rechecked. Systematic errors have been hunted down and eliminated, and still, the disagreement remains. This suggests it might be real, a sign that our model of the universe is incomplete. Perhaps dark energy isn't constant, but changes over time. If dark energy was weaker in the past, the universe would have expanded more slowly then and faster now. This could reconcile the two measurements. Observations of the early universe would see a slower average expansion. Observations today would see faster expansion. But this requires dark energy to behave in ways that current theories don't predict. Perhaps there are additional types of particles or fields we haven't accounted for. Extra neutrino species, for example, or other light particles that were present in the early universe. These would affect the CMB predictions, but not the local measurements. They'd effectively shift the early universe prediction upward. Or perhaps there's something about the early universe, some detail of inflation or the first moments that affects how we interpret the data. A subtle effect that changes the CMB's implications for the Hubble constant. Some physicists have proposed more exotic solutions. Modified gravity, where general relativity behaves differently on cosmic scales. Early dark energy, a component that was significant in the past but negligible now. Or even local voids, regions of lower density that could affect how we measure local expansion. Each idea has challenges. Each requires new physics or unusual conditions. The Hubble tension is unresolved. And it's important because if it's real, if the measurements truly disagree, then something fundamental is missing from our understanding. A piece of the cosmic puzzle we haven't found yet. It might be something small, a detail that slightly modifies our models. Or it might be something profound, a hint of new physics that reshapes cosmology. For now, scientists are pursuing both possibilities. Some are searching for systematic errors, ways the measurements could be reconciled within the standard model. Others are exploring new theories, models that could explain the discrepancy. And everyone is waiting for more data, new missions, new telescopes, new observations that might tip the scales one way or another. It's a gentle reminder, even after all we've learned, the universe still has lessons to teach us, and the Big Bang, well understood as it is, might hold surprises we haven't uncovered yet, questions we didn't know to ask, answers that reshape our understanding of cosmic history. The Hubble tension is a crack in our certainty, and through that crack, new light might shine. The first moments after the Big Bang were dominated by symmetries. In the earliest instance after the Big Bang, the universe was governed by symmetries, perfect balances in the laws of physics that made everything simple, elegant, and unified. These weren't the visible symmetries we see in everyday objects, like the reflective symmetry of a butterfly or the rotational symmetry of a snowflake. These were deep mathematical symmetries in the fundamental forces and particles, symmetries that dictated how reality behaved at the most basic level. All forces were one: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. They were all aspects of a single unified force. There were no distinctions, no separate interactions, just one fundamental force governing all of physics. All particles behaved the same in some sense. An electron and a quark, normally very different, were interchangeable in certain ways, part of the same fundamental framework. The universe was hot enough that distinctions didn't matter. Energy was so high that the differences between particles, the different masses and charges and interactions, were washed out. It was a state of maximum simplicity. Fewer rules, fewer types of interactions, fewer kinds of particles. Everything followed from a single elegant principle. Physicists call this unification, and it's one of the great goals of theoretical physics. To find the simple principles underlying the complex phenomena we observe. In the earliest moments, the universe gave us a glimpse of that simplicity. As the universe cooled, these symmetries broke. One by one, the unified force split into separate forces. The distinctions emerged. The rules became more complex, more differentiated. First, gravity separated. It became its own distinct force, following its own laws. This happened in the Planck epoch, the earliest time we can describe, though the details remain mysterious. Then the strong nuclear force split off. This happened around 10 Kashwasser, 35 seconds after the Big Bang, during or just after inflation. The strong force which binds quarks together became distinct from the electroweak force. Later, around 10 Lewurska 12 seconds, the electromagnetic and weak forces divided. Before this moment, they were unified in the electroweak force. After this moment, they were separate. Electromagnetism, governing light and electric charges, the weak force governing radioactive decay and certain particle interactions. This splitting is well understood. The electroweak theory describes it precisely, and experiments have confirmed every prediction. Each symmetry breaking was a phase transition. Like water freezing into ice or boiling into steam, the universe changed its fundamental state, and each transition released energy, sometimes enormous amounts, sometimes triggering dramatic events. Inflation itself might have been powered by a symmetry breaking, the energy of a field rolling toward its minimum value as a symmetry was lost. And each symmetry breaking created new possibilities, new types of interactions, new ways for matter to behave. Before the electroweak transition, particles were massless. After it, particles gain mass through their interaction with the Higgs field. This changed everything. Massive particles move slower than light. They can bind together. They can form structures. Without mass, there'd be no atoms, no chemistry, no complexity, just massless particles streaming through space at light speed, never interacting, never forming anything interesting. Symmetry breaking is a central concept in modern physics. It explains how complexity emerges from simplicity, how a universe governed by a single elegant principle can become rich with diverse phenomena. It's not just a cosmic event. It happens in many systems. Magnets, superconductors, crystals, all exhibit symmetry breaking. A high-temperature magnet is disordered, symmetric. Cool it below a critical temperature and it spontaneously magnetizes. The symmetry is broken. One direction becomes preferred. The Higgs mechanism, which gives particles mass, is a symmetry breaking. The separation of forces is a series of symmetry breakings. Even the antimatter asymmetry likely arose from broken symmetries. Processes that violate certain symmetries, like CP symmetry, the combined symmetry of charge and parity, could have created more matter than antimatter. In the Big Bang's first moments, the universe was pure potential, perfect symmetry. And as it cooled, that symmetry shattered piece by piece, creating the intricate, structured cosmos we inhabit, beauty giving birth to complexity, simplicity unfolding into richness, and all of it traced back to those first instants when everything was one, when the laws of physics were at their simplest, their most unified, before distinctions, before complexity, before the rules that govern stars and atoms and life. Just pure symmetry, waiting to break. Cosmic variance limits, what we can learn from a single universe. When we observe the universe, we're observing a single realization of cosmic history, one particular set of quantum fluctuations that grew into galaxies, one particular distribution of matter and energy, one particular outcome from the Big Bang. The universe could have been different. If those quantum fluctuations had been slightly different, if the random jitters during inflation had occurred in other places or with other amplitudes, the structure we see today would be different. Galaxies would be in different locations. Some regions that are empty would be filled. Others that are filled would be empty. But the overall statistical properties would be the same. It's like rolling dice. Any individual roll gives a specific outcome, but roll many times and patterns emerge. But there's a problem. We only have one universe to observe, one roll of the cosmic dice, and that introduces an uncertainty we can never eliminate, no matter how good our telescopes become. This is called cosmic variance. The fact that if we could observe a different patch of the universe, or if the Big Bang happened again with different initial conditions, things would be slightly different, and that difference limits what we can learn. Quantum mechanics is probabilistic. The fluctuations that seeded galaxies were random. They followed statistical rules, probability distributions determined by quantum fields during inflation. But within those rules, the specific outcome was random. In another universe, or another region beyond our observable patch, the fluctuations would be different. Drawn from the same distribution, but with different specific values. And those different fluctuations would produce different structures. This means there are limits to what we can learn. We can measure the average properties of the universe very precisely. The overall density of matter, the strength of dark energy, the amplitude of density fluctuations. These are determined by the laws of physics and the initial conditions, and they're the same everywhere. We can test theories by checking if our observations match predictions for these averages. But when we look at specific structures, specific scales, there's irreducible uncertainty. The larger scale fluctuations, the patterns that span the whole sky in the CMB, are affected most by cosmic variance. There are only a few independent modes, a few independent fluctuations at those scales. And we're seeing one specific realization of them. We can't measure their properties more precisely by staring longer or building better telescopes. We've seen all there is to see in our observable universe. The sample size is 1. This is especially relevant for the cosmic microwave background. When we look at the CMB's larger scale features, the patterns that span tens of degrees on the sky, we're limited by cosmic variance. There are only a few dozen independent fluctuations at those scales, and the uncertainty in their properties, just from the random nature of which specific fluctuations we got, is significant. It's not an error in measurement, it's an error in sampling. We have a small sample, and that limits our precision. For smaller scales, there are more fluctuations, more structures to observe. Cosmic variance becomes less important. When we look at galaxies, there are billions to study. The sample is large. We can measure average properties very precisely. But for the largest structures, the cosmic web, the patterns that span hundreds of millions of light years, cosmic variance matters again. To reduce cosmic variance, we'd need to observe multiple independent regions, multiple patches of the universe that evolved from different fluctuations. But we can't. We're stuck with our single patch of space, our observable universe. One outcome from an infinite range of possibilities. If the universe is infinite, there are infinite other regions out there. And in some, by chance, the fluctuations would be nearly identical to ours. In others, completely different. The full range of possibilities exists somewhere. But we can never see them. They're beyond our horizon. Separated from us by space expanding faster than light can cross. It's a humbling limit, not a failure of technology or observation, but a fundamental constraint. The universe has shown us as much as it can from where we stand. To learn more about certain properties, we'd need to be somewhere else, to observe a different patch with different fluctuations, or to run the Big Bang again and watch what happens comparing multiple universes. Both impossible. So cosmic variance remains, a boundary not of technology but of circumstance, a reminder that we live in one specific realization of cosmic history. Not the only possible one, but the one we got. And within that single realization, we do our best to understand the underlying principles, the laws that govern all possible universes, the physics that would be the same no matter which fluctuations occurred. We can't eliminate cosmic variance, but we can work around it, focusing on measurements that aren't affected, building theories that predict statistical properties rather than specific outcomes. And in doing so, we extract as much knowledge as possible from our single, precious view of creation. The strong nuclear force confined quarks into protons and neutrons. In the universe's first microsecond, quarks moved freely through space, unbound and independent. They swam through a hot plasma of gluons, the particles that carry the strong nuclear force, interacting constantly but never sticking together permanently. This was the quark-gluon plasma, a state of matter so extreme that it can barely be recreated in laboratories today. The temperature was trillions of degrees. The energy density was unimaginable, and in this environment, quarks behaved like a fluid, flowing and mixing without forming composite particles. But as the temperature dropped, something fundamental changed. The strong nuclear force, which binds quarks together, began to dominate. Around 1 microsecond after the Big Bang, roughly 10 Etzial, 6 seconds, a phase transition occurred. Suddenly, dramatically, quarks became confined inside protons and neutrons. They could no longer exist on their own. They were trapped, bound together in groups of 3, forming the composite particles that would become the building blocks of atomic nuclei. This confinement is one of the strong force's most important properties, and one of its strangest. At very high energies, when quarks are close together, the strong force is actually weak. They interact, but gently. They can move past each other with relative ease. This phenomenon is called asymptotic freedom, and it's counterintuitive. Usually, forces get stronger when objects are closer. Gravity, electromagnetism, they all follow this pattern. But the strong force does the opposite. Close up, it's mild. Far apart, it's incredibly powerful. At low energies, when quarks try to separate, the strong force becomes overwhelming. The farther apart quarks get, the stronger the force pulling them together. It's like a rubber band that gets stiffer the more you stretch it. Eventually, if you try hard enough to pull quarks apart, the energy you invest doesn't separate them. Instead, it creates new quarks. The field between them snaps, but instead of breaking free, you just create new quark pairs. You never isolate a single quark. They're always found in groups. This is confinement. And it happened in the early universe when the temperature dropped below a critical threshold, around 2 trillion degrees Kelvin. Suddenly, quarks that had been moving freely were locked together in triplets. 3 quarks bound tightly to form a proton. 3 different quarks with different properties bound to form a neutron. The properties of these composite particles depend on which quarks they contain. A proton has 2 up quarks and 1 down quark. A neutron has 1 up quark and 2 down quarks. the arrangement and the interactions between them give protons and neutrons their mass, their charge, their identity. When you try to pull quarks apart, when you invest enough energy, you don't separate them. You create new quarks instead. It's like stretching a rubber band until it snaps, creating two new ends. You never isolate a single quark. They're always confined in groups. This means quarks are permanently trapped. Once they formed bound states in the early universe, they stayed that way. Every proton in your body contains 3 quarks that have been together since 1 microsecond after the Big Bang, bound for 13.8 billion years, inseparable, confined by the strongest force in nature. This confinement transition in the early universe was critical. It created the building blocks of atomic nuclei, protons and neutrons, stable composite particles that would eventually combine during Big Bang nucleosynthesis to form the first atomic nuclei. Without confinement, matter as we know, it couldn't exist. There would be no stable structures, no atoms, no molecules, no chemistry. Just a thin soup of unbound quarks and gluons, drifting through space, unable to form anything complex or interesting. The strong force in that first microsecond shaped the universe's future. It determined what kinds of particles could exist. It set the stage for nuclear physics, for the formation of elements, for the eventual emergence of stars and planets. Everything we see today depends on that moment when quarks became confined, when the universe cooled just enough for the strong force to lock matter into stable packages. And that force continues to hold today. Every atomic nucleus is held together by the strong force, binding protons and neutrons despite the electromagnetic repulsion between positively charged protons. Without it, nuclei would fly apart. Atoms would be just clouds of electrons around single protons. There'd be no elements heavier than hydrogen, no carbon, no oxygen, no iron. The strong force, born in the Big Bang's first moments, remains the hidden foundation of material reality, locking quarks into packages, binding nuclei together, making the complex world of matter possible. The cosmic neutrino background has never been directly detected. Just as there's a cosmic microwave background of photons, faint light left over from 380,000 years after the Big Bang, there's a cosmic neutrino background of neutrinos. These relic neutrinos were created about 1 second after the Big Bang, when the universe was still incredibly hot, but had cooled enough for neutrinos to decouple from other particles. Before that moment, neutrinos were constantly interacting with the hot plasma, scattering off electrons and other particles, exchanging energy, staying in thermal equilibrium. But at 1 second, the temperature dropped below a few billion degrees, and the interactions became too rare. Neutrinos stopped scattering. They began streaming freely through space, and they've been streaming ever since, filling all of space. Calculations predict there should be about 330 neutrinos per cubic centimeter in the universe today. That's comparable to the number of CMB photons, about 400 per cubic centimeter. Neutrinos are everywhere. Right now, billions are passing through your body every second. They came from the sun, from cosmic rays, from supernovae, and from the Big Bang itself. The cosmic neutrino background is one of the most abundant things in the universe. But unlike photons, these neutrinos have never been directly detected from the cosmic background, not a single one. The problem is, they're incredibly hard to catch. Neutrinos barely interact with anything. They're electrically neutral, so they don't feel electromagnetic forces. They're affected only by the weak nuclear force and gravity And the weak force is, well, weak. A neutrino could pass through a light year of solid lead and probably not hit anything. They're ghosts, streaming through matter as if it isn't there. To detect neutrinos, you need massive detectors and high-energy neutrinos. Current neutrino observatories use tanks of water or ice, thousands of tons, instrumented with sensitive light detectors. When a high-energy neutrino interacts with an atom, it produces charged particles that emit light, a faint blue glow called Cherenkov radiation. By detecting that light, scientists can infer the neutrino's properties. But this only works for high-energy neutrinos. Ones from the sun, from cosmic rays, from particle accelerators. The cosmic neutrino background neutrinos have cooled to almost absolute zero. They have incredibly low energy, less than 1,000th of an electron volt. Their chance of interacting with anything is vanishingly small. Current technology can't detect them. It would require detectors far larger than anything we've built, with sensitivities beyond what's possible today. Some proposals suggest using the neutrino's gravitational effects instead of trying to catch individual particles. If neutrinos have mass, which we now know they do, then the cosmic neutrino background contributes to the universe's total mass. Its gravitational effects should be detectable in the large-scale structure of galaxies, or in the cosmic microwave background's subtle patterns. Indirect detection, reading the influence of these neutrinos on other things rather than catching them directly. But they're there. We can calculate their properties with confidence. The temperature, about 1.95 Kelvin, slightly cooler than the CMB. The density, about 330 per cubic centimeter for each of the 3 neutrino types. The spectrum, a nearly perfect thermal distribution left over from when they were in equilibrium. All of this is predicted by Big Bang cosmology and by the physics of weak interactions. And the predictions are consistent with everything else we observe. If we could detect them directly, they'd be invaluable. They carry information from the universe at 1 second old. Earlier than the CMB by hundreds of thousands of years. Closer to the Big Bang by a factor of hundreds of thousands. They'd let us test our models of the early universe's physics in new ways. Measure the neutrino masses more precisely. Probe conditions that no other observation can reach. Check if our understanding of the first second is correct. There are proposals for ultra-sensitive experiments, detectors that might, in the coming decades, catch a glimpse of the cosmic neutrino background, using coherent neutrino scattering, where neutrinos interact with entire atomic nuclei rather than individual particles, increasing the cross-section, or using the neutrino's effects on radioactive decay rates, or even using quantum sensors, devices at the edge of what's technologically possible, to detect the collective gravitational effect of the background. But for now, these ancient particles remain invisible. Silent travelers from the first second of creation, surrounding us but untouchable. Witnesses to a moment we can calculate but not yet observe directly. They were there when the universe was 1 second old, when it was 1 billion degrees, when protons and neutrons were just forming, when the first elements were about to be forged. They decoupled, stopped interacting, and have been coasting through the expanding universe ever since, cooling as space stretched, diluting as volume increased, but never disappearing, never interacting, just drifting, carrying their ancient story, waiting for the day when our technology catches up and we can finally read their message. The multiverse might have emerged from eternal inflation. Some versions of inflation theory suggest that once inflation starts, it never completely stops everywhere. In most regions, inflation ends after a brief period, a tiny fraction of a second. The inflating field, whatever field was driving inflation, rolls toward its minimum energy state. The exponential expansion stops. The energy is converted into particles and radiation, reheating the universe. Normal expansion takes over. This is what happened in our region. Our observable universe is the aftermath of inflation ending here. But in other regions, inflation might continue. The inflating field might take longer to reach its minimum, or quantum fluctuations might push it back upward, keeping inflation going. And in those regions, space continues expanding exponentially. They keep doubling in size over and over, while our region has moved on to slower expansion and normal evolution. And here's where it gets strange. Those regions that keep inflating spawn new regions where inflation ends. Just as our region ended inflation and became a normal expanding universe, new regions do the same. Each one becomes its own bubble universe, its own cosmic history. And the regions that keep inflating spawn more regions, which spawn more regions forever. This is called eternal inflation. Once inflation starts anywhere, it never completely stops. It continues in some places, always creating new bubble universes, forever. This has a dramatic implication. Our universe might be just one bubble in an infinite multiverse. Each bubble would have its own Big Bang, its own 13.8 billion year history, its own galaxies and stars. And the bubbles are separated by regions of space that are still inflating. Regions where space is expanding exponentially, creating more volume, more bubbles, more universes. An infinite cosmic foam. Each bubble a universe. Each one emerging from eternal inflation. Each bubble might have different physics. If the laws of physics are determined by symmetry breaking, by how fields settle into their minimum energy states, then different bubbles might have different outcomes. In our bubble, the electromagnetic force has a certain strength. The electron has a certain mass. The cosmological constant has a certain value. But in another bubble, these might be different. Slightly different values, slightly different laws. Most bubbles would be inhospitable to life. Forces too strong or too weak. Particles too heavy or too light. Constants that don't allow atoms or stars or chemistry. But in an infinite multiverse, every possibility occurs somewhere. The multiverse is controversial. It's not directly testable, at least not with current methods. We can't observe other bubble universes. They're beyond our cosmic horizon, separated by regions of space still inflating. Light from them can't reach us. No signal can cross the inflating space between bubbles. We're causally isolated, trapped in our own bubble, unable to see or interact with the others. Some physicists embrace the multiverse as a natural consequence of inflation. If eternal inflation is correct, and many models suggest it is, then the multiverse is inevitable, not a choice but a prediction. Others reject it as untestable speculation. If we can't observe other universes, if there's no way to test the prediction, is it science? Or is it philosophy masquerading as physics? But there might be indirect ways to test it. If our bubble collided with another bubble in the past, It might have left an imprint on the cosmic microwave background, a circular pattern, a bruise in the sky. Searches have been conducted, but nothing definitive has been found. Or perhaps the properties of our universe, the values of constants and forces, can be explained by being one bubble among many. The anthropic principle, the idea that we observe what we observe because only these conditions allow observers to exist. In a multiverse, this becomes a selection effect rather than a mystery. If eternal inflation is correct, the Big Bang wasn't unique. It's happening constantly, everywhere in the greater multiverse, spawning new universes from quantum foam. Our universe, with its particular properties, is just one outcome. One bubble among infinite others, each with its own history, its own structures, its own story. It's a dizzying thought. The Big Bang, our creation event, our cosmic origin, might be commonplace, a regular occurrence in a much vaster reality. Something happening right now in countless other locations, each creating a new universe with its own fate. And we, living in this particular bubble, can only observe our own cosmic history, one thread in an infinite tapestry, one universe among countless others, forever separated by inflating space, forever alone in our observable patch, forever wondering what lies beyond the horizon we can never cross. The universe's temperature will eventually approach absolute zero. The universe has been cooling since the Big Bang, and it will continue cooling forever. As space expands, the density of matter and energy drops. Heat spreads out over larger and larger volumes. Temperatures fall, asymptotically approaching absolute zero. In the far future, trillions upon trillions of years from now, the cosmos will be cold. Not just cold by our standards, but approaching the lowest temperature possible. Approaching, but never quite reaching absolute zero. Stars will burn out first, having exhausted their fuel. The smallest stars, red dwarfs, can burn for tens of trillions of years, slowly fusing hydrogen into helium. But eventually, even they'll run out. The last star will flicker and die, leaving behind a cooling white dwarf or a black dwarf, a stellar corpse radiating the last of its heat into empty space. Galaxies will fade as their stars die. The Milky Way, Andromeda, all the great spirals and ellipticals will become graveyards. Collections of dead stars, black holes, and coal gas, bound together by gravity, but producing no light. Black holes will evaporate through Hawking radiation, a quantum process where black holes slowly lose mass by emitting particles. This process is incredibly slow. A solar mass black hole would take 67 years to evaporate completely. A supermassive black hole, billions of solar masses, would take 100 years or more. But given enough time, even the largest black holes will disappear, and when they do, they'll leave behind only radiation, particles with ever-decreasing energy, spreading through an ever-expanding space. Eventually, even the longest-lived structures will decay. Protons, the building blocks of atomic nuclei, might break apart. This hasn't been observed, and if it happens, it takes an incredibly long time. Current experiments suggest protons last at least 10 or 34 years, probably much longer. But if they do decay, given enough time, all ordinary matter will disintegrate. Atoms will fall apart. The elements forged in stars and in the Big Bang itself will cease to exist. What remains will be a thin soup of particles, mostly photons and neutrinos, with energies approaching zero. The cosmic microwave background will be stretched by expansion until its temperature is immeasurably low. Right now, it's at 2.7 Kelvin, just a few degrees above absolute zero. In a trillion years, it will be cooler still. In 10 or 100 years, it will be so close to absolute zero that the difference is meaningless. The universe will be dark. No stars, no galaxies, no structures of any kind. Just empty space, vast and cold, with occasional particles drifting through the void, separated by distances greater than the size of today's observable universe. This fate is called the heat death of the universe. Maximum entropy, no energy gradients, no possibility of doing work or creating structure. The universe reaches thermodynamic equilibrium, a state where nothing interesting can happen. No stars can form because there's no fuel. No life can exist because there's no energy to power metabolism. Just darkness and cold and emptiness stretching forever. It's a bleak picture, an ending not with a bang but with a whimper, as the poet said. But it's also incredibly distant, so far in the future that the current age of the universe, 13.8 billion years, is nothing in comparison. We're living in a relatively young universe, an era when stars still burn, galaxies still shine, and complexity still flourishes. The age of starlight, the age of structure, the age when interesting things happen. The heat death is so far away that worrying about it is like worrying about the sun burning out while you're trying to decide what to have for breakfast. It's technically true, technically inevitable, but so distant that it has no bearing on anything happening now or for trillions of years to come. But it's a reminder. The Big Bang set the universe on a trajectory, expansion and cooling, from infinite heat toward absolute cold, from a dense, hot plasma to a thin, cold void. And that trajectory continues, unstoppable, driven by the expansion of space and the second law of thermodynamics. Entropy always increases, heat always spreads out, and in the end, the universe reaches a state of maximum disorder, minimum temperature, and complete stillness. From bang to whisper, from fire to ice, from everything compressed into a point smaller than an atom, to everything spread across infinite space, too diffuse to interact, too cold to move. It's the ultimate fate of a universe born in heat and expansion, cooling forever, approaching but never quite reaching the absolute limit. And in that long, slow fade, we find ourselves living in a brief, bright moment, a flicker of warmth and light in a cosmos destined for eternal cold. The Big Bang Theory is still being refined and tested for all its success. The Big Bang Theory isn't finished. It's not a closed book, a solved problem, a theory that's complete and perfect. It's a living framework constantly refined as new observations come in and new ideas emerge. Every year, telescopes gather more data. The cosmic microwave background is mapped with greater precision. Galaxy surveys map larger volumes, deeper into space, farther back in time. Gravitational wave detectors find new signals from colliding black holes and neutron stars. And theorists develop new models, exploring possibilities at the edges of our understanding, testing ideas that might extend or modify the standard picture. Some recent observations have challenged aspects of the standard model. The Hubble tension, the disagreement between different measurements of the expansion rate, the lithium problem, the mismatch between predicted and observed abundances of lithium-7 in old stars, anomalies in the CMB's large-scale structure, patterns that seem slightly off from what inflation predicts. The unexpected properties of some early galaxies, which appear more massive and more structured than models suggest they should be at their age. Most of these will probably be resolved without major changes to the Big Bang theory. Measurement errors will be found. Systematic effects will be identified and corrected. Models will be refined to account for complexities that were initially overlooked, but some might hint at new physics. Perhaps dark energy isn't constant but changes over time, evolving in ways our current models don't capture. Perhaps inflation happened differently than we thought, with different parameters or different dynamics. Perhaps there are additional neutrino species or exotic particles we haven't discovered yet. Perhaps the early universe had features, structures, or processes we haven't accounted for. Science progresses by testing theories, finding their limits, and refining them. Theories are never proven true in an absolute sense. They're tested, confirmed, and refined. The Big Bang has passed every major test so far. The expansion of the universe, the cosmic microwave background, the abundance of light elements, the age of the oldest stars, the large-scale structure of galaxies, all of it fits together into a consistent picture. The evidence is overwhelming, but scientists remain vigilant, searching for cracks, for places where the theory might fail or need extension. This is how it should be. No theory is sacred, no model is final. The universe is the ultimate authority, and observations are the ultimate test. If new data contradict the theory must change, not the data. Scientists don't defend theories because they're emotionally attached to them. They defend theories because they work, because they make accurate predictions, because they explain observations better than alternatives. And when observations don't fit, scientists are excited, not defensive. Because that's when new discoveries happen, when the universe surprises us. The Big Bang, our best explanation for cosmic origins, will continue to evolve. New chapters will be written, details will be added, nuances refined, gaps filled. Perhaps we'll learn more about the Planck epoch, the first 10 narrowness 43 seconds. Once we have a theory of quantum gravity, perhaps we'll detect primordial gravitational waves and confirm inflation directly. Perhaps we'll resolve the Hubble tension and learn something new about dark energy or the universe's expansion history. Perhaps we'll discover what dark matter is and understand its role in the early universe. Perhaps we'll find evidence of physics beyond the standard model in the patterns of the CMB or in the behavior of particles. It's not a finished story. It's a story still being told, still being discovered, observation by observation, theory by theory, breakthrough by breakthrough. And we're privileged to be here now, in this era of golden cosmology, when technology and theory have advanced enough to probe the universe's origins in detail, adding our own small verses to the cosmic epic, contributing to humanity's understanding of where we came from and how everything began. The Big Bang theory is a triumph, a testament to human curiosity, ingenuity, and persistence. From ancient philosophers wondering about creation to modern scientists measuring the universe with precision, we've come to understand our cosmic origins in remarkable detail. And yet, the story continues. Questions remain, mysteries endure, and the universe, patient and vast, waits for us to ask the next question, make the next observation, take the next step toward deeper understanding. And there, with this thought settling gently like cosmic dust, we reach the end of our journey through 99 facts about the Big Bang. We've traveled from the Planck epoch to the heat death of the universe, from quantum fluctuations smaller than atoms to structures billions of light years across, from the first trillionth of a second to trillions upon trillions of years in the future. We've explored the earliest moments when forces unified and symmetries broke. We've watched quarks confine into protons, atoms form from plasma, and galaxies emerge from quantum noise. Good night.